today, and we recorded yesterday's as well. So I just officially need to let you know.
Cool.
So I want to welcome everyone. My name is Lisa Lancor, and I'm the chairperson of the Computer Science Department here at Southern Connecticut State University. Yesterday, we showed you a video of the campus. If you weren't here yesterday, there will be posted a recording of that as well as all the speakers' slides. So you could feel free to take a look at the recording, and you'll be able to officially visit our campus. We're very excited for day two. Three fabulous speakers, and I'm going to turn it over to my colleague, Dr. Alasheda, who was the person who thought about making an international series on advanced computation and data science. So, Ala, thank you.
Thank you so much, Lisa. So I would like to start by introducing Dr. Merjalili. I mean, we are so glad to have him. He's a big notch in the area of artificial intelligence and meta-heuristic search algorithms. So let me introduce him. Professor Merjalili is the director of the Center for Artificial Intelligence Research and Optimization at Torrens University, Australia. He is internationally recognized for his advances in swarm intelligence and optimization, including the first set of algorithms from a synthetic intelligence standpoint of view, a radical departure from how natural systems is typically understood, and a systematic design framework to reliably benchmark, evaluate, and propose computationally cheap, robust optimization algorithms. He has over 200 publications with, actually the citation that you sent, Ali, was 28. I checked, and now it was 29. 29,000 citation, and with H index of 58. As the most cited researcher in robust optimization, he is in the list of the first 1% highly cited researcher, and named as one of the most influent researcher in the world by the Web of Science in 2019 and 2020. Professor Merjalili is a senior member of IEEE and an associate editor of several leading AI journals, including Neurocomputing, Applied Soft Computing, Advances in Engineering Software, Applied Intelligence, and IEEE Access. His research interests include robust optimization, engineering optimization, multi-objective optimization, swarm intelligence, evolutionary algorithms, and artificial neural network. He is working on the application of multi-objective and a robust meta-heuristic search algorithm technique as well. Please. Thank you.
All right. Thank you very much, Dr. Ala, for the great introduction. And I'd like to extend a warm welcome to everyone to this talk, but more importantly, to the seminar organizers. It's my pleasure to be with you, and I hope that you will find the short presentation that I put together helpful and informative. I'll share my screen. If you can confirm that it is broadcasted now, I can make a start. Can you see my slide, Dr. Ala, and everyone else?
Yes.
We can see it perfectly.
Okay.
Yeah.
Perfect.
Thank you.
All right. So welcome everyone to a short talk on optimization problems and algorithm. My name is Ali. That's my full name. It's a bit long. You're welcome to call me Ali. As Dr. Ala mentioned, I'm director of a center called Artificial Intelligence Research and Optimization. Well, a lot of academics have the luxury of, of inheriting a research center and research group in their career, but I was lucky enough to be the founding director of this research center, and that's why we can see the name optimization in the title. I had to in the name. I had to find a way to fit that in. But anyway, I'm working at Torrens University. It's the youngest private university and overall the youngest university in Australia, 6 years old. And way before everyone used to use Zoom and online meeting, we used to have Zoom meetings across Australia because we have campuses in every major city, 7 campuses across Australia. Now we are expanding to other countries too. But anyway, so in what we are good at in this center, we have a strong team on optimization, and we've been, as you can see on the right-hand side, we've been lucky enough to work with a wide range of researchers across the globe in both science and industry. As I said, today I would like to take you through a journey from optimization problems to optimization algorithms. And this is one of the most overlooked aspect of artificial intelligence and machine learning overall. I look at the optimization, as you know, optimization problems are everywhere. Any area you look into, people try to improve something, whether it's a process, whether it's a system, whether it's a workflow. People usually want to optimize it to maximize a certain objective or minimize a certain objective. So the first part of my talk, I will take you through the most fundamental elements of any optimization problem, from finding an optimal path from here to Mars and land a rover to design a small device in a nano level. They all have the same key elements and fundamental elements. And after going through those fundamental elements, I will then talk about optimization algorithms. I'm not going to put my finger on any specific algorithm, but I'll give you enough I'll give you enough background. I'll talk about the status of this field and the sort of algorithm and the major shifts that we've seen in the last in the last decade. And the reason why I start with problem, a lot of people ask us why we don't talk about algorithm and you always start with problem. Because to me, an optimization algorithm doesn't do, in order to use an algorithm, we really need to know a problem. And the analogy that I always give to my student is a lock and a key, right? If you lock out, if you forget your key in your house and you're locked out, you don't go to a keysmith and ask to give you a key, right? You need to, of course, get them to your door. They inspect the lock, and based on the type of lock that you have, they will build a key for you, or they use some sort of tools to open the door so you can grab your key. What I'm trying to say is that a lot of people come to us and ask what the best optimization algorithm is in 2021, 2022, and moving forward. Well, to me, that question is fundamentally wrong because we need to know the problem. And that's why the very first thing I ask everyone to do when they come to us from industry or from academia is to really sit down and think about the elements that I'm about to introduce to you. Yes, after we identify those, we can then think, okay, now we can find the right solution, right algorithm for you. So my presentation is quite generic. I focus on optimization problem, but I will try to put it around the context of data science, because I noticed yesterday there was a lot of talks around data science, machine learning, and today also we've got quite interesting talks coming up. But and that's why at the beginning I said optimization is probably one of the most overlooked aspects of data science and AI. I assume what we do in optimization is like an engine to a car. So I consider ourselves as a back-end developer who design the engine, and there's a lot of front-end developers who design fancy products and services to the customer. So let's start with optimization problems. Any system, I'm going to use the term system, that refers to any sort of system that we're trying to optimize. The first component on the left-hand side, as you can see, is the set of inputs. These are the decision variables that we are trying to find the best values for. These are unknowns. We don't know the best values for them. And different combination of the inputs will give us an output, okay, which is often called objective. Some people refer to a cost function, fitness function, and so on. Basically, this is an output of the output of a system. The third element, which is quite important and a lot of people overlook it, is a bunch of constraints. Usually, designers come with us with constraints because, okay, we might be able to find optimal solutions for them, But if those solution doesn't violates the constraint that they are mindful of, then that's the solution is no longer valid. So after identifying those three elements, and as I said earlier, any optimization problem from optimizing, the shape of a rocket to optimizing something at the nano level, they all have those three fundamental elements. And after we identify them, we can formulate the problem. Without the loss of generality, I formulate it as a minimization problem. As you can see down there, F, which is the output of the system, is a function of x1, x2, xn. Those are the inputs, the blue color, subject to a number of constraints. Okay. And this is where an optimization algorithm comes into play, right? So often an optimization algorithm, and definitely the recent one, the one that we usually work on, they assume a problem as a black box, which means we don't need to know what's inside the problem, what's inside the system, I should say. We don't need to know how people wire the system. All we need to know is, okay, what sort of outputs we get by manipulating, by changing the inputs, while keeping an eye on the constraints. Yes, there are some algorithms also that required a bit of information inside the box. Those, for example, gradient descent. But for us, as I say, in black box optimization, we assume no knowledge of the problem. Okay. So as you can see, there is a difference, a clear, you can draw a line between an optimization algorithm and an optimization system, or the problem that you're trying to optimize. Okay. So a quick example of, before I give you a very small, simple example, in neural network, for example, the learning, usually in the field of machine learning, the learning process is an optimization. What are the inputs of your system? Those are the connection weights and biases, and basically the structural parameters of your artificial neural network. What is the output? Output can be mean square error. It might be classification accuracy, prediction rate, and so on. What are the constraints? Those are the constraints that you might need to focus on. For example, some of the weights might be restricted in a certain range. Okay? And then, of course, we have the wide range of learning algorithms, which are technically optimization. And that goes back to the point that I made earlier, that an optimization algorithm is the engine of a lot of AI techniques that you've been using and you've seen and you've heard a lot. Okay, but a lot of people are not aware of them because, as I said, because this is the backend. Okay, there are so many tools that you can grab. There are out-of-the-shelf tools that you can use, but at the bottom layer there is definitely an engine and a learning technique, which is an optimization algorithm. All right, so let's take a look at a very basic example. The reason why I've chosen this example is to show you what we are trying to do when we define an optimization problem. Because you might often hear about, a search space, search landscape, and those kind of fancy terms, but at the foundational level, it's nothing more than it's common between all optimization problem. And I'm about to show you in 2D, and I'm a very visual person. You will probably see in my slides that I've got a lot of visualization. But I want everyone to have that sort of understanding. And once I've gone through those, I'll talk about the state of the art in each of those areas as well. Let's say we want to design a table. There are so many parameters, number of legs, thickness of the material that you use, and so on. I've chosen two parameters only, length and width. Let's say someone asks us to optimize this problem, and the objective is the output of the system, which I name it here weight. It can be any other, of course, objective. This is a hypothetical equation. I didn't want to make it complicated, just a linear length plus width times 1. What are the inputs? The inputs are both, of course, both of them, both the parameters that we identify. There are a bunch of constraints given to us by designers, and the output is the weight that we are trying to minimize. Okay, so the objective is to minimize the weight. Now, so after identifying those three key elements, we can now formulate this problem. We are trying to minimize a function of length and width, subject to, not violating the constraints that you see down the bottom over here. Okay. Now I want to show you what happens now. What we've done just now in this slide is basically to define something called a search space. I'm about to draw something quite interesting that is applied to any optimization problem. In the x-axis, I've got the width, the first parameter. In the y-axis, I've got the length, and in the z-axis is my objective. So I've got this plane, x and y plane, shows me the inputs of the system. The z-axis shows me the output. Okay, so of course, both width and length can be any continuous number between 1 and 10. I assume. Did I assume it's between? Yeah, it's between 1 and 10. That was an assumption. So, but for the sake of data visualization for now, I assume they are discrete values between 1 and 10. The first design that we can come up with is where width and length both equal to 10. It's going to be this corner, this point, the maximum point. Next is where one of them is 9. Those are the 2 points on the sides. And the next solution is where both of them are equal to 9. And we can keep going. If I keep changing those inputs, okay, these are 8 more designs for this problem. These are 50 more tables, and now we've got 100 tables. Of course, we have 10 values for width and length. The maximum number of design is 100. But I made that assumption that those parameters are discrete, but in fact, in reality, those are continuous parameters, right? So for this very basic problem, even for this hypothetical problem, we are dealing with a search space that includes that has the potential to give us an infinite number of solutions. Okay. Now you can think a bit broader. In any optimization problem, you can increase the number of parameters. Okay, it depends, of course, the problem that you're trying to solve. And in that case, there will be an n-dimensional space, right? N minus 1 dimension are allocated to the parameters, and the last one, assuming that the problem is single objective, is for the objective. Okay, and this is called a search space. Search space is the decision variables, all the possible combinations, which is in this case infinite. A search landscape is where we associate those solutions with with an objective value. Okay. Of course, for this very, very basic problem, any linear optimization algorithm will, quickly converge to the bottom of this landscape, right? So the best design from this perspective, without considering the constraints, is where the table is the smallest table with width and length both equal to 1. But remember, we had also constraints, right? We had also constraints. If we apply the constraint, the search space is much, much smaller, right? So now that we managed to draw the search space, now which one is the best solution for this designer, for this client? Of course, the one that I highlighted in purple with a purple arrow down there, where width and length are both equal to 2. Okay, but remember, there are so many other solutions that might be as good as this one, but definitely that is the best one, which is what we call a global optimum for this single objective optimization problem. Okay. But real-world problems are not that easy. Think about training artificial neural network with thousands of connection weights, thousands of structural parameters. What we are dealing, and a lot of constraints in that case. Usually, what we are dealing with is a search space that looks like this. Again, I have to show you a 3D space here, which is X and Y and an objective. But I want you to think much, much broader. Think about an n-dimensional search space with a large number of parameters and objectives. Okay. So often, as you can see, there are separated regions. There are so many locally optimal solutions. There are, there are deceptive regions that leads you toward local solutions. And that's the complexity that we usually face when we solve optimization problems. Okay. And again, in data science, all the learning process is exactly what we do. Okay. And often when your neural network doesn't converge, it's because you get trapped in one of those small local solutions. Okay. Now I might just maximize this, so because it looks much better. Now I'm going to spend probably 5 to 10 minutes to talk about the state of the art in each of those components that we've talked about just now, including inputs, constraints, and the outputs. And probably if we have, some PhD students on the call, I might give them some direction, for research if they're interested in this area. So one of the complexities that we usually deal with is the large number of decision variables or the inputs. Okay. Yes, there is no, there is no threshold saying, okay, if you have over this threshold, your problem is large scale. It really, it totally depends on the problem that you are trying to solve. But for us, a lot of existing optimization algorithm struggle when we apply them to a lot of problems with large number of variables. Okay, so there is a field of study called large scale optimization, which look into the challenges in that space. So we try to come up with techniques to handle this at the algorithmic level, which means we find the variables that are correlated, find some sort of dependency between them, try to reduce the search space, because if you can, because at the moment the existing technology that we have in terms of software and hardware doesn't allow us to cope with that challenge in the best manner. Yes, there are so many solutions out there, heuristic based, but what I'm saying is that there are always a bit of uncertainties involved. Yes, there are so many quality assurance along the way to ensure the quality of the solution, but still there is so many room to do more research in that area. A few more difficulties that we face here. Variables with different rates, and by the way, a large number of decision variables is something data scientists deal with when they are training a neural network, particularly deep learning. As you know, in deep learning we have so many layers, we have so many connection weights, and the complexity. You definitely deal with a large number of parameters to optimize. Variables with different ranges. I show you a rectangular, square shape. I should say a rectangular square shape search space, but you can think about when the range of variables are different, the search space is no longer rectangular, or I should say hyper-rectangular. It might the shape might change significantly when you change the range of variables. Some problems have variables with significant different ranges, which makes a lot of algorithms struggle because they haven't been designed to cope with that kind of discrepancy between their variables. That's the sort of thing that often people find difficult to handle when it comes to decision variables. Dependency between the inputs, as I mentioned, discrete variables. As you know, when your parameters are discrete or binary, your problem is no longer continuous. You are dealing with a combinatorial optimization problem. And you know that just like other machine learning, just like other discrete problems, we are dealing with a large number of states in such problems. And the curse of dimensionality is real in that space too. We've got combinatorial optimization. It's a subfield of optimization. If you think about it, a big umbrella of optimization, we have combinatorial optimization. A large portion of that is combinatorial, and that was the beginning of a lot of old-fashioned, a lot of traditional optimization algorithm designed to solve combinatorial, and then later on extended to other types of problems. Problems with mixed variables, mixed integer. You might have heard of mixed integer optimization problem. That's the area that people try to address. Some of the parameters are different. Some binary, some discrete, some continuous. That's a bit of complexity that you might find as well. And last but not least, an area that I've done a lot of research in the past, and my PhD was on noisy optimization, or we call them robust optimization. The problem in this case, the complexity in here is that, okay, often we use simulators, we use models, sometimes meta models when we try to optimize a problem. And even if we use a simulator, which is quite accurate, when we give it the final design to a manufacturer, there is always production errors, right? Even if it's 0.00001, that might lead to significant deviation in the expected output. And that might be problematic. Imagine if it's a lift of an aircraft and suddenly it deviates substantially from what you would expect in simulator, that might result in a crash. So the area that we do there are so many techniques. I don't have the time to get into the details. What I'm trying to say is it's a very relevant area. There's this fairly recent area in particularly in the meta-heuristic and heuristic field. And if that's a complexity that you're dealing with in your problem area, whether in data science, machine learning, artificial intelligence, or any other field, as I said, optimization problems are everywhere, you should be looking at the literature of robust optimization. Okay, and to me, any real world problem that we solve and will be solving in future should be optimized and should be solved considering any sort of uncertainties that are involved, because we can minimize the impact, the negative impacts that they might have in the expected output of a system. Now, moving on to the constraints, just like the variables, often real-world problems have a large number of constraints, which makes them so very challenging to deal with. The more constraint you have, the smaller your search space becomes, and the more difficult for an optimization algorithm to solve it. So there are so many, we've got a lot of researchers across the globe and research centers working on constraint handling techniques, which allows you to handle complexities around constraints. You can, for example, you can handle them at the problem level to use some sort of penalty function and so on, or you can solve it. You can address it at the algorithmic level, which means the algorithm is the one who make a decision based on the constraints as well. Constraints of a problem might be an equality constraints or equality constraints. Equality constraints are much more difficult to meet because of the nature of them. Inequality are a bit easier. Again, you might have problems with mixed equality and equality constraints. Those are the challenges that people deal with when they work on real-world problems. Yes, a lot of test functions that we use in optimization field are quite easy to solve. They've been designed to test either, for example, a constraint problem with just inequality or equality. Just recently, in some competition in CEC conference or WCCR conference, people started to have those kind of complexity combined in one test bed or test suite, I should say. But what I'm saying is that in real world problem, you are sometimes deal with a lot of other complexity combined. What I mentioned about the parameters, what I'm now talking about constraints, and what I will talk about objective later on in the next two slides. So overall, what I'm trying to say is that constraints is also a quite, there is it's a very active area, subfield of area, and we can't overlook them. They are very important, and usually that's how designer gives us preferences, okay? Because we help them to formulate the problem, but then what sort of solution they want us to find, that's with constraints, they dictate their priorities and preferences to us as optimization, as algorithm designer, I should. Just a quick example of showing you how difficult just changing an equality constraint to equality makes the problem. See, I've got now, imagine a designer asks us now, okay, I don't want rectangular shape. I want square shaped table, which means I want only the table that width and length are both equal. So basically, as you can see, I've got here subject to length and width equals to 1. So that with that simple equality constraints, the search space substantially gets substantially smaller, right? Now think about an optimization algorithm. Often you end up, around this narrow line, so you have to, discover at the first hand to be able to even converge to the best solution down the bottom of this plane. Okay. And usually the real world problems, what we are dealing with is something like this. As I said, you have dominant, the invisible region of the search space, which is where you violate the search. At least one of the constraints is dominant, which means which makes it substantially harder. And there's a term that we use, isolated island. If you think about it now, for an algorithm to find the best solution, which I cut out here, that's the best solution. It needs to swim across the ocean between different islands. in an attempt to find the best solution. And there is no clue sometimes, right? There is no clue, okay, as to where the best solution is, because we've got a lot of, infeasible regions on the way. I'll give you an example. I was working with an industry partner for a problem in the area of computational fluid dynamics. It was to design optimize a compressor blade in jet engines. As you know, those kind of problems are heavily constrained. We were using a variant of genetic algorithm, and as you know, a genetic algorithm, we have different generations, we have a population. Even with a population of, I think it was 200 individuals, and even across 500 generations, we were not able to even find a single feasible solution. That means we constantly, jump from one of these white areas to the next. So we ended up, creating a framework. So we started with some of the standard design that they have in the Boeing company, and then we started from those solutions. So that means we had some clues where those islands are, so that helped the algorithm at least to start the search process, let alone to converge in the end towards the best solution. So that's what you find of also in machine learning data science. Often the problems are heavily constrained, and that's why if you use an learning algorithm, if you use an optimization algorithm, you should be mindful of that. If you apply a learning algorithm or optimization algorithm, it doesn't give you a result straight away. That's because that's often because of the constraints. Now, moving on to the third key fundamental component of any optimization problem, which is called outputs or objectives. Okay? One of the most fascinating areas of optimization, which I'm always interested in, multi-objective optimization. Right? To me, any problem, right, on this planet, any optimization problem is multi-objective by nature. And even if you think about your real life, you solve a lot of optimization problem, and in fact, you always consider multiple objective, right? And that's a complexity, because when you have more than one objective, sometimes those objectives are in conflict, right? And that's what makes decision making a bit difficult. Even at the algorithmic level, you are dealing with solutions that have a trade-off, and they contradict each other. So which one you choose best, which one is the best solution, that goes back to decision maker at the end. What I'm trying to say now is that that's a complexity that a lot of people deal with. And often, again, in the field of data science, there are multiple objectives. For example, in artificial neural networks, yes, one objective is usually to minimize the error rate of the system of the network, but often also, because we have so many layers, we have so many hidden nodes and etc. You also need to optimize the structure. You need to minimize also the connection weights and biases that we have, to be able to probably to prevent overfitting or underfitting at some point, mainly overfitting here. What I'm trying to say is that this is a challenge that people face with, and if that's also what you face in your problem, you should be looking at the literature review of I should say, multi-objective optimization. There's so many techniques there. I'll show you an example in a moment, but I just wanted to highlight the fact that this is quite challenging. And to me, well, now at the moment with the existing technology, we get to the point that we can handle up to 4 or 5 objectives. But the problem is that when we increase the number of objectives, every solution that you find is a good solution, because you are considering multiple objectives. So the area which is a very recent area and very relevant is called it's called many objective optimization. And the reason why we use the term many objective, because we refer to the fact that it's around more than 5. Again, it's hard to put a threshold for these kind of things like statistics, but people tend to struggle when you have 5 objectives. One of the reasons is, of course, high dimensional data visualization as well, which is always the case in any field. But the main problem is the fact that when you have a large number of objectives, every single solution that you find might be good. So you can find sometimes you need to bring decision maker to the loop to be able to give you some weight so you can combine them. Sometimes you need to maintain the formulation, but try your best to keep it at the multi-objective level, not many, to be able to use the existing algorithm. The objective of the third complexity is dynamic objectives. In a lot of problems, time is also plays a key role. For example, in self-driving cars or robotic navigation or robot navigation, path planning, and stuff like that, or image processing, video processing overall, the search space that you have changes over time. You can think about an ocean. If you look at this search space, you might think, okay, it changes over time, which means if my algorithm was looking around this solution, now this will move towards a set different location. Sometimes it significantly changes over time. There is an area called dynamic optimization. This is a software level optimization, which is what we do. We try to keep track of the changes in the search space. We try to use some meta models to be able to, to handle this complexity. There's so many techniques there. It's out of the scope of this talk to go through the details. But I'm giving you enough, directions. If that's the problem that you are dealing with, which is often in the field of image processing, video processing, and that's the sort of complexity. So you should be looking at dynamic optimization. And as I said, the main complexity at the moment, which we just started to work on in my research team, is large scale optimization. A problem with a large number of objectives. So just to give you a quick example, as always, I really want you to have a visual understanding of this. Think about it. In a multi-objective problem, you have multiple of these. This is one objective. You might have multiple objectives. It's like, if you can imagine, it's like a car racing in multiple, let's say a football team playing in multiple games, multiple fields at the same time. It's very, it's a lot more difficult than a single objective. Here's a quick example. Let's say now I'm going to optimize also the price. I want to minimize the weight and also the price. And again, a hypothetical equation, price is a function of length and width. We just multiply them. Now, the problem is that, take a look at these two tables. The left one, and we keeping in mind that we are trying to minimize both of them, weights, and the weight of the table and the price of the table. The left one is 2 kg, but $100, probably made of a good with a good finish, and it's a very expensive luxury product. Not that luxury, but what I'm saying is that the quality is good. The right one, however, is 5 kg but $20. But the question is, which one is better? It really goes back to you, right? If I'm looking for a cheaper product, definitely the right one is something for me. Doesn't matter if it's quite big, heavy to carry. I don't care as long as it's cheap. But for you, it might be the quality that is important, and the final finishes, the final touches. In that case, you might go say, okay, that's fine if it's a bit more expensive. I'm gonna go with that as long as it's a bit lighter, because I want to be able to carry it around in my house if I need it. So the problem is that we can't compare the two. So what we need, people use a Pareto optimality, which is basically allows you to find the best, compare at least solutions in a multi-objective search space. According to the Pareto optimality, a solution is better than the other if it shows equal objective in all of them and at least one better in one of them, I should say. So take a look at these two tables. The left one is 5 kg, $10. Definitely that's better than the right one because it's heavy and expensive. No one buys this for sure. Left one, this one, 5 kg, 5 kg, the weight is similar, equal, I should say, but the left one is cheaper for sure. You can now make your decision and choose the left one. Down the bottom, same story, but the opposite this way, $10 both, but left one is lighter. So definitely the one on the left is better. But often that's what you're dealing with. You don't know. And the example that I always give to people is to buy a laptop. When you are trying to buy a laptop, it's often quite challenging. Why? Because, okay, if you just look at the RAM, of course, you can maximize it, but then the price also arises. If you look at the CPU, the faster CPU, the more expensive. So there's always a trade-off. Now I've got CPU, RAM, hard drive, price, and they're all the function of cost. Cost is a function of all of them. It's always difficult, and you are the one who choose. If I'm a graphic designer, then I'm going to buy a one with a decent, let's say, graphic card. If I want to do computational activities or task with it, then I'll choose a one with a decent CPU. That all goes back. Yeah, at the end of the day, a lot of people believe that any multi-objective problem can be converted to a single objective if we know decision-making preferences. But for me, as an algorithm designer, we don't know usually that sort of information. So what we do, we will find the set of solution that are the best, that represent the best trade-offs between the objectives. Okay? And that in that case, we'll leave that to decision maker. We're going to say, look, these are all the possible tables that I came up with. They're all good tables because because they have the best trade-offs between cost and the weight. You choose the one that you want. If your customer wants luxury product, then you can choose this one, for example, this product, this design. If you're looking for other type of other customer demographic, you might choose the one in the middle. That's what we do with people. That's why we, as an algorithm designer, we usually, if we don't have that sort of knowledge, we try to find the best trade-offs. Just quickly, let me just check the time. I'm running out of the time, so I'll be quick. And then, so now that we know what the optimization problems are, and I've given you enough, I've also talked about the state of the arts and also the challenges that we face as in this area. Now we can move on to the optimization algorithm. I'm going to be a bit biased here. Quick disclaimer, because every now and then I get some mathematician in the audience, because I use the term conventional and modern, or traditional modern, and that refers to a lot of mathematical optimization algorithms that are out there. They're still very important, very relevant, and quite effective. But I'm a bit biased towards meta-heuristic and heuristic because that's the area that we work on. And a lot of real-world problems, particularly the ones that are nonlinear and we don't have gradient information of the search space, we have no choice but to use heuristic, but to make educated decision, which is heuristic. Okay. So one of the most popular, widely used conventional optimization algorithm that you might have seen is gradient descent. We know that if we calculate the gradient of any search space, that leads, and if we follow that step by step, that leads us to global optimum. That optimum is not necessarily global if you start from a wrong point. If you follow the negative of the gradient, that leads you to the best value or the best minimum in the vicinity. Okay. Now the problem that we have with such traditional optimization algorithms is the fact that they are good for linear. I shouldn't say linear because that's not really linear. There's a bit of curve here. But a problem with the unimodal search space. What does that mean? That means we have only one global and one local solution. In these kind of problems, there is no locally optimal solution as opposed to the ones on the right side. So if your problem is this type of problem, I would never use, any sort of linear optimization algorithm, and in this case, gradient descent algorithm, will be helpful because it allows you to quickly and efficiently converge towards the global optimum. But in real world problems, that's not the case. That's what we are dealing with. These are not efficient for unimodal landscapes. If your starting point is not good, is not of high quality, then chances are you end up with inside a trap, which is a locally optimal solution. So that is where modern optimization algorithm, which I'm going to use the term heuristic, meta-heuristic, or stochastic, whatever you want to call them, comes into play. As I said, because of the limitation of conventional optimization algorithms, and also the complexity of optimization problems that I mentioned earlier, we need to, it's not viable to use those kind of algorithms in a wide range of problems. So that is where we bring that sort of educated decision. And if you think about it, in the way that our brain works is not usually exact, right? We make decision based on uncertainties. We make decision based on fuzzy logic. we make decision based on a lot of factors, okay? And we are surrounded with environmental conditions. Things might change in a fraction of a second sometimes. Think about when you're driving, you constantly make a decision, and you know, and do actions and make a decision and perform actions based on the environment around you. So to me, stochastic techniques try to, and a lot of nature-inspired optimization algorithm that my team has developed, or other researchers developed, they try to bring that sort of, you know, stochastic behavior and educated decision into the mix, right? And that's why I said, to me, stochastic methods are quite are very applicable because of the issues that I mentioned in the last slide. Just a comparison between those two classes, deterministic versus stochastic, or traditional versus modern. The advantage of a lot of optimization algorithms, traditional ones, is the fact that they are reliable in finding the same solution. Yes, we have stochastic gradient, we have a wide range of improved version, but they are a bit more reliable in finding very similar solution each time. They require less number of simulations and function evaluation, which means they are computationally cheaper, and they are quick. They benefit from fast convergence. But some of them might not work in their favors, because those might lead to local optimal stagnation. They have low chance of finding the global optimum in heavily constrained problems, in problems with a large number of locally optimal solutions, etc. They heavily depend on the initial solution, and they mostly need derivative of, they require calculating derivative of the search space, which is not viable in a large number of problems. On the right side, the advantages of heuristic methods or stochastic methods: they can better avoid locally optimal solution because of that random, that stochastic nature. They have high chance of finding the global optimum because they show more chaotic behavior. It's not 100% chaotic and random, of course. It's one side of the spectrum is exact, one side is pure chaos and 100% random. It's somewhere in between, that it's a fine balance between the two, that, you know, you hit the sweet spot, and then you know, your algorithm is able to find a reasonable approximation of the global optimum. They are not really dependent on initial solution that much as the left class, and they don't need gradient descent. However, they are quite slow, and they're computationally more expensive. They find different answers in each run. And that's why there's a lot of, you know, debates in this area, and between two communities, you know, about those pros and cons. And to me, future is the marriage of the two fields, and meta-heuristic and, you know, mathematical optimization algorithm overlap often a lot. And to me, the future is the marriage between the two. And at least with the existing technology that we have, who knows what will happen when we have quantum computers. With that existing technology, computing powers that we have, and then the best solution is the crossover between both of the fields. The reason why you've heard a lot about meta-heuristic, things like genetic algorithm and so on, is I mean, the reason why they are popular to me originate from those two benefits. They can better avoid local solution, less probability of being trapped in those solutions, and they benefit from gradient-free mechanism. Now, before I finish off, I'm almost done, and I'm cautious of time. I've got 5 minutes left. So now you might have seen there's a lot of algorithms recently in both areas, in both communities, and you might be asking, okay, what's the end of the line? Are we gonna ever have an optimization algorithm that solve any optimization problem? Well, there is a theorem just in machine learning. In machine learning, you might have heard of no free lunch theorem. We have very similar in optimization. So according to this theorem, and this theorem logically proves that there is no optimization algorithm to solve all optimization problems. And that's what keeps this area of study quite active. Any area, any problem, that any class of problem, and as humans we keep, you know, and we keep increasing the complexity. I mean, what I'm trying to say is that the complexity of the problem that we face keeps increasing, and and the growth is exponential. So to cope with those challenges, the new type of problem that we face, the complexity, we need, to change the algorithm that we have. We need to adapt them. We need to tune them. We need to hybridize them. That's exactly what we do in the field of optimization overall and heuristic mainly. So that's why we see a lot of algorithms recently. They are, good. Usually they're designed to tackle a certain group of problems, and that's why when you go to different communities, you might find, a cohort of, researchers using a certain algorithm because they group around the problem. If your problem is similar to mine, definitely the tools that I use might be helpful for you as well. I had a bit of a slide about, the challenges in simulate and stuff like that. I might just leave it there. But that's all I wanted to cover for this short talk. It was, again, just a quick summary before I take some questions. Well, it was all about optimization problems and algorithms. In the optimization problems, in the first part of this talk, we learn and we talk about, the challenges, the recent challenges, state-of-the-art techniques in optimization. And then we ended up talking about algorithms. I didn't want to get into the details of any of those algorithms, but I gave you enough. So now you know that those are communities, those are different areas, different types of algorithms out there. You just need to, explore, and based on the problem that you have, you can always find there's an algorithm out there, right, waiting for you to be discovered and help you to solve your problem, probably better than any existing techniques out there. That's all from me. If there is any question, I'll be happy to take.
Ala, you're muted.
Thank you so much, Ali, for this wonderful lecture. It really covers a great deal of optimization, and it can work as a roadmap. If somebody would like to go for optimization, he can know where to go. There is a question actually here in the chat room.
Sure.
It says, do I make it work and then optimize? And what is the best time to implement or begin an optimization?
Let me just read the question. So what's the best time to implement and begin on optimization? Are we talking about the problem? Possibly here, do I make it work? And then, well, look, that goes back to what I mentioned earlier. Look, to me, and that's what we usually, ask our students, right? When they are taking an exam or a quiz, we keep saying, read the question multiple times, because if you don't understand the problem, right, you might end up with the wrong answer. That's exactly what I recommend people to do when they have an optimization problem. I said, look, spend a couple of weeks to think about those fundamental components, right? Come with me, and we tend to sit down with them and grab a piece of paper, identify those key elements, the decision variables, the objectives, the constraints, and how how your problem relates the input to the outputs and where the constraints sit in. So to me, when you have a good understanding of your problem, that is where you can look for a solution, right? Look for an optimization algorithm to optimize it, okay? So don't start looking for an algorithm until you have a clear understanding of your problem. And don't get me wrong, it is often an iterative process too, which means you go and solve it, you go back and think about your problem, because sometimes you have a large number of decision variables. You make that educated decision. Say, I want to focus on the first five. I want to skip over. I want to ignore these for now. Use this bunch of constraints. It's an iterative process, but the stepping stone to a successful, to a successful project in that area is to understand the problem. So, yeah. There's another one. From the same person, I think, Kalika.
Yeah.
If you cannot optimize without a problem, so I'll need to build it first. Let's last. Yes. So, well, yes. Sometimes the problem is there. You need to, or you are given the problem, like you have a client, right? they want to optimize, let's say, the compressor blade. They have a model there already. They have a simulator. You just need to sit down and see what sort of new, angles they want to take. But you're right. So if you don't have, as I said, my analogy first, um, you cannot find a key without a lock, a good key without. Yeah, you can go and grab a bunch of keys, but when you don't have a lock, you're wasting your time and money probably to buy those keys, right? Definitely. So you need to find the problem and then optimize.
In fact, I have a question. Uh, it's about the dynamic landscape or the dynamic fitness function.
Mhm.
Now, a long time ago when I was at Mason and we keep discussing dynamic landscape, which changes as a function of time, we had a big problem here on doing the optimization, especially that evolutionary computation and meta heuristics like work offline, not online.
Yeah.
So can you give me like some solution for this problem or recent development in that area?
Yeah. So we that's a great question, Dr. Alla. So we are dealing with two challenge, which I didn't mention. I briefly touch on it, but now we added another difficulty. The first one is the dynamic change of it, right? It's like you are a hiker and you're trying to find the highest or climb to the highest mountain, but then suddenly you teleport from one world to the next world, right? Yeah, that's a
Yeah.
complexity. And look, people use meta model, people use multimodal optimization, which means in optimization algorithm we have exploration, exploitation. They maintain a certain level of exploration over time and keep it all the way to the end of iteration, just to make sure that they don't lose that capability, because you can easily get trapped, right, and assume this is the best one, although it changed. But I think what you were referring to is the time, because it takes time, right, to
Yeah.
converge, and then by the time that it converge, the search space changes 1,000 times in the meantime. Well, that goes back to what I mentioned about the problem, and one of the drawbacks of stochastic methods or population meta heuristic of to be to in particular, is because it takes some. So that's where people try to tune the algorithm, let's say, to find, let's say, um, first of all, in terms of software and algorithm, yes, there are some parameters that you can optimize, which means, let's say, the number of population, so the population size, the number of generation, etc. Or sometimes you can find a reasonable solution quickly with those algorithms, but then apply a gradient descent algorithm to converge quickly. So it's a fine balance between the two, right?
Yeah.
That's one thing. The other thing is you can also, so that's at the algorithm level. At the problem level, you can sometimes, people tend to use meta models as well, which means they the search space, they run the experiment first. They train some sort of machine learning to learn the changes in the search space and feed back to the algorithm. So it's a bit of data-driven optimization as well. So those are the two areas that might be helpful. First one, it's to reduce the computational cost. Second one is to really ensure we can keep track of changes in the search space and don't wait until it's too late.
Do you think, Ali, if we look to this problem or consider some assumption that assuming we have different operating conditions for the system to reduce the complexity, and for each operating system we could have like a landscape that we can optimize, do you
Yeah,
think
so
that?
so that's so it's not multi-objective, but what you're saying is that you might have multiple parallel, right, landscapes.
Yeah, yeah,
You're trying to search, and maybe one of them is what you're looking for. Absolutely, but I'm not too sure if that's gonna. We need to sit down and see whether that's gonna drastically increase the computational complexity of the problem, which will go back to the first issue that you mentioned. But definitely, look, the other thing that I forgot to mention is hardware, right? High perform parallel processing is something you need to, of course, leverage on, because of this time is important, right? Which means, like if I can have one CPU, one node of CPU allocated to each of the generation, then I can easily converge. So but you're right. That's what you mentioned as well is one one interesting area to explore for such problems.
All right. Thank you.
Yeah.
In fact, I have another question, but if somebody else has a question, we can
Yep.
take
So
it.
I think Binling Wu mentioned asked a question. Could you elaborate a bit more about the stochastic optimization method in contrast to deterministic? Do we simply start with random initial condition and find deterministic solution for all condition and compare? Look, I was just trying to classify those algorithms overall, optimization algorithm, into two categories, being deterministic, which means there is no educated decision along the way. You make your decision based on gradient information all the time, in case of gradient descent algorithm. But in stochastic, you're trying to bring a bit of randomness. Even we've got a stochastic gradient, isn't it? Where you can randomize the initial point each time. But if you are asking about the key differences between the two, well, the randomness, the stochastic nature is what makes it different. And you're right. Sometimes you start with a random population, and overall, that's the old framework. They start with a set of random solution, and they improve the quality of those solution over time, just like what nature does to any chromosomes and genes, right? We inherit the best but nature select the best gene over time based on the environmental condition. That's just one example of an algorithm. So hopefully that answered your question.
Yeah, of course. Yes,
Yeah.
yes. So I just want to ask a quick one.
Sure.
About the simple subpopulation idea, like the migration.
Mhm.
I remember William Spears. He was a classmate a long time ago, and he started this idea in his class project, which is like decomposing the population to number of subpopulation and
Mhm.
then do migration. How
Yeah.
this idea is developing nowadays? Because I didn't see much work in this area.
So we call them in what you described reminded me of subswarm, right? In
Yeah,
the field of swarm intelligence. Well, there is a lot of research going on in that space because, as you mentioned, one these are the challenges that people face. One, how to create those swarms, how to spread them, around the search space to ensure to maximize the possibility of finding a global solution. That's one challenge. Second challenge, how do we then combine, or how do we share
migrate.
information between the subswarm to be able to, find some clues and improve the chance of finding the global optimum. The other one will be, okay, at which stage of optimization it's better to form them into one swarm as opposed to subswarm. But the problem that you mentioned in dynamic optimization, usually people benefit from subswarm and they don't measure them at the end, right? They keep all the subswarm, just like imagine a group of bees, right? We have a swarm, but they have small subswarm going and foraging on different part of the landscape. Yes, they collaborate, they communicate at some point in the hive, but at the end of the day, they are the one who go and forage. So absolutely. So there are so many things, so many there are active researchers and active research project in that space. But those are, again, if I wanted to focus on the complexity, those are the sort of things that. But the recent one that grabbed my attention was to use some sort of data-driven decision making, which means the swarm also learn from the search space, which means based on the improvement over time and the quality of the changes in the search space and their position, they then learn for the next optimization, the next run, which means we pass information not only between individual subswarm, but also between different generations and different runs, which is something we don't usually do, right? We always start from scratch, right? It's
Yeah,
like reinventing the wheel each time. It's
yeah,
definitely wiser to keep all the information like a database of, sample point, and learn from them. The next time that we face this similar problem, similar search space, they have clues. Like, just like what happens in nature, at some point, insects, ants, they get adapted to the environment. They know where things are because of the pheromone that deposit. They don't do it every morning. They don't start to, do everything from scratch. They keep track, they learn over time. So Absolutely. So machine learning, bringing machine learning into that sort of subswarm is quite recent, something interesting to look into.
Thank you so much. Thank you so much for this
Yeah.
wonderful
All
lecture.
right.
And it has
My
been a pleasure
pleasure.
to have you. Thank you.
Thank you so much. Yeah, I'm happy. I think I've already shared my slides. My website is there. If you have any questions, anyone from the audience, I've got a contact form there. You can always get in touch with me, and I'll be happy to continue our discussion offline.
Thanks again. Thank you so much.
Thank you so much. Have a great rest of day, and see you all later. Bye-bye.
See you.
Thank you,
Take
Professor
care.
Ali. Thank you.
Thanks. Bye.
Thank you. Okay, so our next speaker is Dr. Faris.
Hi, Dr. Ala. Hi, how are you?
How are you, Hassan? How's it going?
It's all great.
Yeah,
Thank you.
all right. Okay, so we have Dr. Hossein Faris. He's a full professor at King Abdullah II School of Information Technology at the University of Jordan and the School of Computing and Information and Computing and Informatics at Al Hussein Technical University. Professor Faris is also the director of data science at Al-TB, the largest digital health provider in the MENA region. He received his BA, his bachelor, and his master degree with excellent rates in computer science from Yarmouk University and Al-Balqa Applied University in the years 2004 and 2008, respectively, in Jordan. Since then, he has been awarded a full-time competition-based PhD scholarship from Italian Ministry of Education and Research to pursue his PhD degree in e-business at the University of Salento, Italy, where he obtained his PhD degree in 2011. In 2016, he worked as a postdoctoral researcher with Geniur team at the Information and Communication Technology Research Center, University of Granada. His research interests include applied machine learning, evolutionary computation, knowledge-based system, and data mining. Professor Faris has about maybe 5,500 citations, if I remember correctly. Please.
Thank you, Dr. Ala. Can I share my screen, please?
Yes. Would you like help Hassan to share it or what?
No, it's okay.
You have share
I can
rights now.
Okay, you are
Yeah.
now okay, great.
Can you see my screen now?
Yes, we can.
Okay, great. Okay, thank you, Dr. Ala, for introducing me and for the invitation. Thanks also for the organizers. I am very happy to be here with you today. My talk will be about advanced applications of AI and data science in telehealth, developed by the data science team in Al-Tibbi, which is one of the largest telemedicine companies in the Middle East and North Africa region. And I will talk also about the main challenges that face the development and improvement of these applications. Okay, so for the outline, the outline of this presentation will go as follows. I will talk briefly about telemedicine, then I will give an overview of the context of this presentation, which is Al-Tibbi Telemedicine Company. Then I will talk about the main data sources in Al-Tibbi, and then the effect of the pandemic on the demand for telemedicine services and its data. Then I will introduce briefly the data science roadmap and some of the main AI and machine learning projects developed by Al-Tibbi and the challenges that we face. Okay, actually there are many definitions of the term telemedicine. One of the simplest ones I will quote from the World Health Organization is healing at a distance, which signifies the use of information and communication technology to improve patient outcomes by increasing access to care and medical information. Actually, there are many reported advantages for telemedicine, and many of you already know it really good, which include reducing inappropriate health interventions, reducing hospitalizations, a better care aligned to patient and family needs, decreasing total health spendings, and having a healthier and more supported population, of course. Talking about the context of this presentation, Al-Tibbi company, just to give you a brief background about it and about the AI and machine learning models that will be introduced. I will talk a little bit about Al-Tibbi. Al-Tibbi is one of the largest digital health platforms in the MENA region. It was launched in 2011 in Amman, Jordan. The platform provides telemedicine services and simplified medical information to users in the region in Arabic language. These telemedicine services allow patients to connect directly with doctors via audio calls and text chats. The main goal of Al-Tibbi is to increase people's access to quality primary health care. So for developing an AI and machine learning based application, we are interested, of course, in data, because without data we can't build a machine learning model. Data in Al-Tibbi comes from different sources and comes in different forms and formats. So we have the website, the user app, the doctor app, and the clinic app. From the website, we have medical articles, videos, labs and drugs information, medical calculators, and many others. From the user app, there are questions asked by the users of Al-Tibbi as text or as calls, and they can upload files like lab tests and images and so on. The doctor app is used by Al-Tibbi doctors to write recommendations and answering the patient's inquiries and their questions. By numbers, we are talking about 20 million users over the platform, 1 million pages of Arabic content, more than 10,000 doctors, and around 3 million medical consultations. We can see here how huge the data is in Al-Tibbi. Let's talk a little bit about the effect of the pandemic. With the COVID-19 outbreak in the MENA region, Al-Tibbi witnessed a huge demand for the service. This figure shows the dramatical increase in the number of consultation per month on the platform. In fact, Al-Tibbi covered around 2 million consultations from March 2020 till January 2021. Of course, this increase of consultations and traffic comes with opportunities and for sure challenges. On the other hand, acting quickly based on innovative plans and strategies for scaling up and facing these opportunities and the challenges is vital for staying a strong competitor in the market and the business. And consequently, and therefore, Al-Tibbi responded quickly at different levels to face these great challenges. And you can see here in the figure, starting from March 2020, the number of consultations we are receiving Al-Tibbi is increasing dramatically compared to the time before. One of the major decisions the company took in the last 3 years was the decision to establish and start a data science department. It was officially structured after around 18 months of preparation and building skills and capacity. The data science department started with well-defined roadmap that includes a wide set of AI and machine learning projects with an estimated timeline for each project. So the company designed a data science roadmap with the aim to improve the quality of different processes and services across the company at different levels, based on the state-of-the-art machine learning and deep learning technologies. Basically, the main use cases for the developed AI and machine learning in Al-Tabbi can fall under different forms, like for example, insights generations. Just to give an example on the insight generations, like for example, a churn prediction or user churn prediction. Another example is the operational effectiveness, like automating quality control of consultations and telemedicine smart routing. Also, another example, adding features to an existing product or feature in Al-Tabbi, like specialty detection, supportive diagnostic module here, okay, and supportive treatment module. Those we will talk about later. The products even can have even a form of a new product, like iDoctor bot. So we have different forms of these machine learning projects. Here we can see the main projects that Al-Tabbi started and included in our roadmap. Some of them are already finished and deployed, and some are under development, and some are still to be developed in the near future. So here's the wide set of machine learning projects. And in this presentation and in this talk, we will focus on those framed in red: the supportive diagnostic module, specialty detection module, automatic quality control of consultations, and COVID-19 calls forecasting the number of calls we receive related to COVID-19 on the platform. Okay, so for most of these AI and machine learning projects, a standard methodology is usually followed for the development, starting by defining the task, then defining data sources, then performing exploratory data analysis, then we go for feature engineering, then training the machine learning models, and finally evaluating them. Of course, the process is iterative, based on the evaluation results, similarly to many methodologies used in data mining. So let's talk about the first project, the specialty detection module. As we saw before, thousands of medical and health questions are received on daily basis on the platform from the patients. For each question, a specialty should be determined, meaning that under which medical category this question falls. We have to classify the questions into specialties. Previously, and in a classical way, a team of general practitioners manually direct the patients to the right specialized doctor. Actually, this consumes a huge amount of time and effort, as you know, or as you can expect. So we built a machine learning classification system to automatically classify medical questions into the correct medical specialty, and to save time and effort for the operation team or the general practitioners. As you know, one of the main exploratory data analysis is visualization. Here we performed, before developing the model, we applied a technique called TSNE. This was done in order to have an overview of the complexity of the problem and the relationship between the features. TSNE, which stands for T-distributed stochastic neighbor embedding, is a nonlinear technique for dimensionality reduction that is particularly well suited for visualizing high-dimensional datasets. We can see from the figure here many overlapping specialties. Let me show you here with the pen. As you can see here, this area is related for or represent the dental medicine. Okay, this class, and you can see it has a very clear shape. While on the other hand, there are other specialties that they are really mixed with the other classes, and they overlap strongly, and it's really hard to differentiate them from the other classes. Like, for example, this class, or let's see this one here, the light green. Okay, as you can see, it's very hard to separate them or separate it from the other classes. It's really overlapping. There is a strong overlap between some specialties. This is really due to common characteristics and keywords used in phrasing the questions related to these specialties. For example, you can see some questions of two different overlapping classes that they have very similar and very many words in common. This makes the problem more complex and harder. So the basic blocks or the basic algorithms we use in this module is the TF-IDF, the classical one for feature representation. For classification, we use support vector machine, and for as a multi-class strategy, we use one versus rest. As you know, this is very simple classification module, and many advice in machine learning. When you want to start a project, you go for something quick and dirty, just to get something very quickly and see the potential of your data in getting good results. So we started with this with these blocks, really simple ones, and then we improved the classifier later on, and I will show you how we improved this classification model at different levels. This is, I know this framework could be or could look somehow complex, but believe me, it's very easy and simple. We use a particle swarm optimization for optimizing different hyperparameters. You know, we want to apply support vector machine, and we have this hyperparameter, the cost. And for TF-IDF, we have another two hyperparameters, the minimum document frequency and the maximum features threshold. All of these hyperparameters were tuned using the famous particle swarm optimization stochastic search algorithm to automatically tune the parameters and evolve the classifier. So to show you the confusion matrix we got after applying this, after testing our classifier, you can see here the performance according to the all classes. We can see the results summarized in this confusion, and there are misclassification between very overlapping classes. If you can see here, for example, the sexual health. Okay, we got 199, and we misclassified the 21 cases. Okay, this misclassification was a confusion between the sexual health and urology class. Okay, these 21 instances were classified as urology. If you examine the questions under both classes, you can see they have many terms and let's say keywords used in common between both classes. Here we can see that the proposed model achieved better results in terms of classification accuracy compared to other common techniques, and the average accuracy was around 85% over all the classes. We compared here with different classical algorithms, classification algorithms. So then we try to improve the previous model at two different levels. At the feature presentation level, using word embeddings, and the classifier level, using deep learning approach. So let's talk about the new approach or the new improved model. In the new model, we used, rather than a small, very small data set, which was around 15,000 in the previous support vector machine model, here we used 1.5 million unlabeled consultations we use them for training the embeddings for feature representation, and then we use 75,000 questions for the classification and for the training of a deep learning model. The proposed question classification model here depends on a variation of deep learning, which is the LSTM model for specialty detection. So we experimented different types of word embedding techniques based on word2vec, based on Keras, Arabic, and Altabby-vec. 4 types of word embedding. The basic idea of word2vec is that similar words used in the same context will have similar vector representation and consequently higher similarity scores. Also, Keras offers an embedding layer that can be used for neural networks on text data. The embedding layer is initialized in Keras, is initialized with random ways, and will learn the embeddings for all the words in the training dataset. On the other hand, Arabic is a pre-trained word embedding. Trained or pre-trained, we mean already built and shared openly on the web by other researchers. And Arabic was trained based on Arabic language. There are different versions of Arabic built based on Arabic content, like Twitter and Wikipedia. On the other hand, Altabby-vec is a word embedding for Arabic language trained based on the medical and healthcare context developed by Altabby. We developed this our own word embedding because we want to capture the personality, let's say, and the specific characters of the text we have in Altabby, because they say each context has its own language. So if you train a word embedding, a general word embedding based on a Twitter or Wikipedia, it will not be really effective in the healthcare, because in healthcare or telemedicine we have a different characteristic of the scientific language you use to express the questions, the recommendations, etc. So after constructing the embeddings of the data, we trained LSTM and bi-LSTM models as deep learning models for the specialty detection. Let's see the accuracy we got after training the bi-LSTM and the LSTM. We achieved around 87 average accuracy over the whole classes. If you compare this accuracy to the previous one, we can see we got an improvement of 2%. This 2% could look very small here, but in the context of our operations, it has its own value. It's worth to go for deep learning and word embeddings, to go for these improvements we stated here to get or to reach this accuracy. Talking about a little bit about the challenges we faced during the development of this model. First is the complexity of the Arabic language itself. And also the majority of the questions are written in dialect. Most of our users come from the Levant countries, Egypt, Saudi Arabia, and the Gulf in general. So you can see there is a big variation between the dialects, and people are used to express their questions or inquiries in their dialects, and building a model based on these dialects is still very, very challenging. Also, there are specialties are extremely hard to correct, classify, and declassify due to the small number of instances under these specialties. They are rare classes, and you can see an imbalanced distribution in your data. Another challenge is that some questions could be multi-labeled. Like one question could fall under more than one specialty, but we formulated our machine learning model or a problem as a one versus rest. There is an independency between the classes. So this makes a problem here. As one last challenge we can talk about here is that some specialties have questions that are very easy, very similar syntactically and semantically to each other. Let's now talk about the second module, which is the supportive diagnostic module. In this project, the data science team in Al-Tabbi built a multimodal machine learning model to predict the diagnosis of a patient condition based on the symptoms documented in their electronic records and the question of the patient. When we say multimodal, we mean that the data are coming from two different sources: the unstructured question received from the patient and also the symptoms identified by the doctors. For this module, around 260,000 of questions were used along with their specified symptoms and diagnosis from our previous historical data, and the total number of different symptoms and diagnoses included in this model is around 7,000 for each. Each consultation is assigned multiple symptoms and multiple diagnoses, even that some of them infrequently occur, meaning that they are rare symptoms and diagnoses. And the international classification of diseases, known as ICD-10, is used to codify the symptoms and diagnoses in our dataset. So as you can see here in the diagram, two machine learning models were built based on the questions of the patients and symptoms independently. Then a fusion of the prediction was made for final prediction. For the first model, different feature representation techniques were used, like TF-IDF, as we mentioned before, very classical approach, hash vectorizer, available in scikit-learn and Python, and document embeddings like Word2Vec, Aravic, and AltaBVec. The fusion of the predictions of the two models was done using different schemes based on their scores, the scores of the models, we mean. The multiplication, the types of the fusion are multiplication, the ranking, and the summation of the scores we receive from the two submodels. The multiplication fusion method achieved best results. With a prediction at 1, we mean precision at 1 means here that we at least we correctly classified one diagnosis. The accuracy was for this case 85%. And as you can see, the same applies for precision at 2 and precision at 3, meaning that at least we classified correctly 2 diagnoses and 3 diagnoses respectively. And also the accuracy for all cases for precision at 1 was above 80%, and it was reasonable for precision at 2 and precision at 3. Talking now about the challenges for this module, the SDM, there are two main challenges we can talk about here related to the SDM module, which are the associations between the diagnoses are not detected by the followed strategy here in developing the machine learning model. Because we use a multi-label, multi-class using one versus rest. One versus rest breaks the association between the classes, and we build a classifier for each class, for each class of the 7,000 we mentioned before. The second challenge is that rare diagnoses are extremely hard to detect because they are underrepresented in our data sets. So we don't have enough data to train our machine learning model. Let's go and talk about the third module here. Al-Tibbi works with expert doctors from different specialties to monitor, evaluate, and provide regular feedback to Al-Tibbi doctors to improve the quality of the service. All new doctors on duty are closely monitored in Al-Tibbi for 2 weeks after they join the company. All their consultations are reviewed and evaluated by experts against defined measures. If no errors are detected, they are allowed to take a higher number of medical consultations, and then they will be evaluated regularly later. The expert doctors, the evaluators, assign a level of quality for each consultation evaluated by a rating from 1 to 5. They give a score for each consultation. These levels were proposed to capture the overall impression on the quality of the consultation. So 5 stars, and 1 the lower quality and not really high. So this module is to automatically evaluate. We are proposing this module to automatically evaluate the quality of the medical consultation provided by the doctors over voice. Before this, assessing the quality was performed manually by the operation team. They sample the medical consultations like audio recordings, and they listen to these recordings, and then they score it. We developed this model based on deep learning mechanisms and the combination, and by combining two submodules. The first submodule, as you can see here in the figure, converts the audio signals into text and then analyze them, while the second analyzes the audio signals, meaning signal processing, and extracts a frequency and spectral-related characteristics. Then we combine them into a hybrid model, like we have also two different models, and we make a fusion between the predictions. So talking about the first submodule handles the problem by analyzing their transcripts, meaning that the recorded audio consultations are converted to transcripts using Amazon Transcribe service, and then the text is processed and features are extracted and presented as words and word embeddings. The constructed dataset based on the transcript is then used to train a series of convolutional layers, then max pooling layers, and a fully connected layer. All this pipeline formulate one deep learning model. The second module here, based on the recordings also. The recordings are divided into segments of length of 60 seconds. Three distinct types of features commonly used in the literature were extracted from each segment, then averaged over. The types are the famous MFCC coefficients, the spectrogram, the zero crossing rate, and other beta features. The prepared dataset was divided into three subsets: the training, the testing, the validation, as usually performed in machine learning. The training and validation data used to train and tune stacked deep learning feed-forward neural network with a different number of neurons at each layer, as shown in the figure. This was for the second module. Then a hybrid approach was developed based on these two submodules. Here the figure shows the structure of the developed model, which mainly combines the two models of the signal-based and the transcript-based and their outputs. The concatenation of the outputs from the two submodels is done by adopting a concatenation layer. As you can see here, the concatenation layer concatenate the output of the two, the two submodels. The output of the concatenation layer then is fed into two stacked dense layers. The last layer is output layer to produce the probabilities of the output classes. All of these configurations, of course, were experimented based on a long series of experiments, because we have here a large set of hyperparameters, like the number of nodes, the number of layers, and so on. The results of the hybrid model shows a precision of around 40%. This percentage could look very small, but here it means that if we sampled 100 recordings, audio recordings of the consultations happened between the patient and the doctor, then 40 recordings will be of low quality if predicted by our machine learning model. Before, it was much lower than this. Our operation team was spending a lot of time. For example, if they sampled 100 recordings, they will find, for example, maybe 15 recordings usually. Okay, but now with the support of this machine learning model, we are getting around 40 recordings if we sampled or we predicted the defected or the low quality consultations with this machine learning model. This improved the detection rate over the classical approach, of course, but still it is not really satisfactory, and we are trying to improve this percentage using different approaches. Talking about the challenges for this module, the labeled dataset actually was relatively small. It was around 2,000 recorded labels. We know a larger dataset might improve the model's performance, but actually evaluating the codes and labeling them takes really considerable time and effort from our operation time. They really spend a lot of time doing the labeling and the scoring process. Another technical challenge here is that the calls are recorded at low sampling rate. When we started this project, we found that most of our recordings are recorded at low sampling rate, that is 8 kilohertz, while 16 kilohertz is more recommended to capture various spectral and statistical features. It is even recommended for many state-of-the-art speech models. However, this comes with extra storage. If we want to address this comes with extra cost for storage, and we should experiment the traffic under the pressure. You know, we will have a higher pressure on the traffic. On the other hand, talking about another challenge, there are many speech models already built for modern standard Arabic and some of its dialects, but we still don't have an excellent speech model for a mix of dialects, like when we have, like in our case here, a call, for example, a call between an Egyptian doctor and a Saudi patient, for example. Now we have, for example, a mix of dialect, and it's really hard to transcribe such a conversation with a very high accuracy. The last project that we will talk about is the COVID-19 calls forecasting module. This is a very interesting project for us. Like in many other countries, Al-Tabbi, in association with the government in Jordan, released the COVID-19 hotline. We call it 111 in March 2020 to answer the calls related to COVID-19 inquiries. A team of doctors answers these calls daily, 24/7, and motivated by the need of the operation team to schedule enough doctors ahead for this critical task, deep learning models were developed for forecasting the number of calls related to the COVID-19. So our users or anyone who has an inquiry or a question about COVID-19, he can call the hotline 111 in Jordan, and he can ask about COVID-19. We handle this line in Al-Tabbi, and we developed this machine learning model based on deep learning to forecast the number of calls we will receive next day or 2 days or 3 days. We will talk about this now. The deep learning models we developed are based on variants of recurrent neural networks, very famous ones like LSTM and BIAL-LSTM. So the data used for training the forecasting models are the number of daily coronavirus confirmed cases in Jordan, announced by the Ministry of Health. And the other variable is the number of phone calls that we receive over the hotline. So let me show you the trend of both variables over time. The daily confirmed cases and the number of calls. Here the figure shows the number of daily coronavirus confirmed cases in Jordan, as we said, okay, announced again by the Ministry of Health in Jordan. It is shown in a blue color, and the number of phone calls that were received by the hotline of Al-Tabbi in orange color. As you can see, it can be clearly noticed here the high correlation between the two variables. There is a high, like the trend is really similar. When we have more calls, meaning there are logically there are more cases. There is really a high correlation between the two variables. So the question is, can we use the number of cases announced to predict the number of calls we will receive the next day, so we can reschedule our team doctors or not? So we explored different forecasting models based on different number of lags for both variables, the number of daily confirmed cases and the daily number of received calls. Actually, we took 7 lags for each variable. Overall, we got 14 models to experiment. This is another diagram that shows the architecture of the forecasting model. It is important to note here that we tried to forecast for 3 prediction horizons: 1 day ahead, 2 days ahead, and 3 days ahead, denoted as C here down. The results for the LSTM are represented here in this table. We can see that model M8, based on just 1 step lag for both variables, is the best performing model, especially for 1 day step prediction horizon, with 97% correlation. We got really good result for 1 step ahead, but still a little bit challenging for 2 steps and 3 steps. Okay. Here we can see the actual number of calls versus the estimated number based on the best BIAL-STM model we trained for 1 day ahead forecasting horizon. In general, the model, as you see, the model shows satisfactory results for this time horizon, but for longer horizons, for 2 days ahead or 3 days ahead, the error gets higher, and it's not practical, and the problem gets really more challenging and complex. Once you increase the horizon, the prediction horizon, of course, the problem gets more complex and more challenging. As for the challenges for this case, more attempts for increasing the accuracy of the model can be studied by including other factors, like, for example, the frequency of some related terms to COVID-19, search in Jordan using the search engines. And this idea, I think, was mentioned many times in the literature review, assuming that, for example, if more people search for terms related to COVID-19, then there are more infected cases. On the other hand, another challenge is that increasing the prediction horizon, as we mentioned earlier, and maintaining a good accuracy for these prediction horizons is very difficult. However, if we achieve that, then this will give the operation team a chance and more time to schedule their shifts and the shifts in general of doctors, and properly estimate the number of needed doctors ahead in a better way and save time and effort. To summarize, in general, there are challenges inherited in our work from the complexity of the Arabic language itself, and especially when it comes to the use of its dialects, as we mentioned earlier in the specialty detection model. Other challenges we can mention here include the lack of open datasets in Arabic healthcare. It is well known that sharing and openness play a significant role in the advancement of of scientific research. However, and on the other side, privacy of critical data like patients' records is extremely important. Now, from a machine learning perspective, interpretability of the developed models is very important and is considered as one of the main principles of AI in healthcare. And in many situations, interpretability and understandability of the model is at highest priority when it comes to evaluation. In this, we can summarize the main challenges we face during the development of our machine learning models can fall under these main lines. I would like here finally to refer you to our list of publications we published based on the experiments we conducted while developing our machine learning models presented under these projects. So for more technical details, you can refer to our published papers on the presented AI and machine learning models, and I would be happy to share them with you. So thank you all for listening. I would like to thank my data science team also for their dedication and for their incredible efforts in building these AI and machine learning projects that serve the company at different levels. I would like also to thank Dr. Ala for the invitation and the organizers for their efforts in designing and their efforts in general in designing this event. Thank you very much, and I'm ready to take any questions related to this talk.
Hala, you're muted.
Okay, thank you so much, Hussam, for this wonderful talk. I mean, it's very exciting, especially when you talk about medical applications. So I know this is a challenging area, and I know you have been working for this maybe in the last couple of years. So that's a wonderful work. Thank you so much.
Thank you, Dr. Ala.
So we have some question in the chat room. Um, I think one question, how is forecasting COVID-19 cases for the coming few days beneficial? Uh,
Yes,
Another
as I
question?
stated before, we can I answer this question?
Yeah, please.
As I said before, we have an operation team who decide how many doctors we need to address the calls we receive at LTB. So if we manage to predict accurately the number of doctors we need for tomorrow for addressing the calls and to respond to people, we will, of course, help the operation team to determine the number of needed doctors in order to handle the calls.
Yeah, that's great. I'm not sure, Sam, have you taken in consideration some attribute like closing? You know, in Jordan, there is always closing on Fridays. There are closing in, you know, like 6 p.m. in the evening, everything. Does this make any effect to the forecasting model?
Yes, Dr. Ala, of course. We just finished this project. We finished this project recently, just a couple of weeks ago, and development and the improvement is still ongoing for increasing the accuracy for 2 days and 3 days forecasting horizon. And it's very challenging, as I said before in the presentation. If we need to get higher accuracy for the next 2 days or 3 days, we need to include more features, like as you say, maybe that including holidays, for example, or specific events. If we included these features, I believe we can even have a better accuracy, and it's still worth investigating, of course.
Thank you. Lisa, is there other questions?
Yes, I see a question. Dr. Ferris, what type of diagnosis do you aim to make using computer vision?
Yes, we try to predict a differential diagnosis at the lowest level at the ICD-10 coding system. We use ICD-10 coding system to codify the diagnosis we receive. So based on the last 3 years, we received a large number of medical consultations and all represented using ICD-10. So we built this machine learning model to predict the differential diagnosis at the lower level. And if you can refer to our paper on this topic, you can see different examples for this.
I have a question, Hussam. It's about the pre-processing of the data. I mean, you had a huge number of record, and do you do any kind of like segmentation for the text or even for the recorded messages, something like that? I mean, using deep learning also?
Of course, in most of our projects, which are based on text, we use extensive pre-processing because any machine learning model, if you want to build it based on text, you need to clean the text from, for example, stopping words, extra characters, special characters, and so on. There are many details on the pre-processing stage, especially for Arabic language, and you need special techniques to handle this process. And it's really time-consuming. Um, the more time and the more effort you spend on the pre-processing stage, the more or the better results you can expect at the end after applying deep learning approach. We conducted different experiments and relation between the extensivity of work on the pre-processing stage and the results we get after applying deep learning. We saw really high effect of the pre-processing, especially on Arabic language. And once you are talking about a mix of dialects, the thing goes even much more complex.
There is a question from Anton, and Anton, I wonder if you can just unmute yourself and ask your question. That might be easier to have the conversation, or if you don't have a mic, I could ask it. Or Hosam, if you see the
Yes.
chat. Yeah, okay, go ahead. Thank you.
Sure. Can you hear me?
Yes.
Yeah, sure.
Okay, cool. So my question was regarding your second project. You basically mentioned the problem of rare diagnosis, and I mean that this is the general issue in context of precision medicine, and in general, the AI and ML models as supportive tools should serve to help the clinicians to improve their diagnostic decisions. So, in case of rare diagnosis, the standard ML approaches lack in their accuracy. So my question is, how is your opinion or approach to tackle this problem, specifically to improve the supportive power of AI and ML tools in case of a rare diagnosis, or basically in inbuilt data set?
Yeah, I totally agree with you. We have a great difficulty identifying rare classes or rare instances fall under rare diagnosis. Of course, this is very challenging, and our data is most relevant to primary care. You know, like most of our users looking for primary care, and most of our data related to common diseases like flu and things like this. So identifying this is very challenging, and we are exploring different approaches to try to boost the performance of our algorithms for detecting rare classes or diagnoses. There are different approaches. We are exploring approaches at the data level, like oversampling, undersampling, etc., and at the algorithmic level to increase the cost for our deep learning approach related to these specific classes. So we are still experimenting this. And thank you for the question. Really great one.
Thank you very much. And may I ask another question?
Yes, please.
Regarding your third project, so basically, what was your definition of poor quality consultation? So it was mainly regarding the low quality of recording, or lack of the symptoms explained, or what was your definition of poor quality consultation?
Yes, thank you for the question. I got your question. Honestly, the definition was one of the challenges in this project. Our operation team, they have a set of standards, they have a set of criteria, they evaluate the recordings based on them. In our machine learning project, we assumed to have an average of all these measures. So low quality recordings can include interruption, maybe some bad attitude in the quality in the recording, and so on from the doctor side or something like this. So there are different metrics and criteria used to evaluate the quality. For simplicity, in our machine learning model, we made an average in the label. We took the average of the ratings and we use it, and even we simplify it. At the beginning, it was, if you notice in the presentation, um, we had five ratings from 1 to 5. Then we tried to take 4 and 5 together to refer to high quality or good quality, let's say, and 1, 2, and 3 to indicate a low quality. So with this approach, I told you we didn't really reach a satisfactory result. It was around a precision of 40%. In our next step, we will try to break down the definition of the quality, as you mentioned, to interruption, bad attitude, for example, and so on, and build a machine learning model for each one. And we expect a good result because you have a specific class to predict. Thank you very much for the question. Really, really smart one.
Thank you very much for your answers and good luck in your work. Thank you.
Thank you. Thank you.
Thank you so much, Hassan, for this wonderful talk. And please, everybody realize that we have the form is available in the chat room, so please fill it out. Thanks a lot. And
Thank you, Dr. Ala. Thank you.
Thank you so much, Hassan. And now we move to our next talk by Professor Mirello from Grenada. Hey, okay, great.
Hi.
Glad to have you. So Professor Mirello has his PhD degree in physics from University of Granada. He has been working since 1988 as a professor, eventually since 2009 as a full professor at that university. He's a strong supporter of open science and free software, being part of the RACU Steering Committee Council since 2020. His main research interests are in parallel computing, complex systems, machine learning, and computational intelligence.
Support and for your
Please, Professor.
I can't share my screen, I'm afraid. I don't have the share button is still grayed out. So, okay, now I can do it. Thank you very much. So first of all, thanks a lot for inviting me to this very interesting seminar. Dr. Sheta, I'm really grateful for this, and I am also very grateful to Hossam, who's a colleague of mine, and he was here in Granada for some time, for inviting me over. I mean, for me, this is going to be a real interesting chance to present my ideas, not only in data science itself, also science in general. So this is this is why I'm going to talk about, how to we are going to put the science back in data science, or we are going to learn from data science to actually carry out science in a totally different way. I'm going to tell a personal story here. Well, first of all, you already know that I'm professor at the University of Granada. This is Sebastian Cobb. He's a character in The Simpsons, and he's the one that actually created the monorail. And we're going to talk a little bit about The Simpsons throughout the talk. And I have been programming since 1983, but since then I have been learning a lot. But in the last 2 years, I have learned, I think, much more than I did. Why? Well, basically, I have 2 daughters. They are twins. They are both computer science students. One of them has been working for a software development company for 1 year and a half already. And we always, since the pandemic, we have breakfast together. We always talk. And my other daughter started just a short time ago to work in a data analysis, data science company here as an intern. I talk to them all the time, and I'm learning quite, lots of things. And I realize that they know so much that we don't, that it's just amazing. I mean, it blows my mind. I put everything together with my experience, and I think I will try to come up with, I would say, a way of doing science that's maybe a little bit better for everyone involved, because I am in academia. I think that people in the companies are doing things much better than we do. But why? Can we do as well as they do? Well, let's see. First thing is, everything started with, kind of started with this, right? So this is a paper we published last week. It's called The Simpsons Did It. It's exploring the film trope space and its large scale structure. It's publishing in PLOS ONE. I mean, you can check it out. This is open access. This is part of a research that's related to the PhD of a person, Ruben, who's working on this. And basic idea is that we're going to automatically generate narratives, right? So that's the end objective. That is what we're going to do in the end. So, we have been following many different phases, 7 years already. So it's long PhD, as they usually are. But in the beginning, what we have are tropes. We need a bit of background on that. We have tropes. Tropes are basically things that you repeat over and over again, and we take them from TV tropes. So TV tropes is a kind of a wiki. It's actually a wiki, right? So it's like the Wikipedia for popular culture, and we work with data that was contained in that website, with everything that involves, right? So we had to scrape it, we had to work with it, and so on and so forth, right? But that was something that we had at the beginning, right? A trope. What is a trope? Well, it's a repeated motif or pattern in fiction in general. Sometimes you find them also in real life, but they are not stereotypes. A bad trope is a stereotype. Good trope are usually archetypes. So the basic idea is that it's going to be repeated in fiction. For instance, I don't know if you see here at the left-hand side, you see a silhouette on the moon. You probably recognize that trope immediately. It's from E.T., right? It's actually a trope. It's called silhouette on the moon. And it's been repeated over and over again in many other movies, right? So that's part of the makeup of a movie, and that's something that we would like to, work with. There are many other tropes. If you are able to recognize every single thing in this mural, which by the way is in Platzi, it's a company that's devoted to creating courses, you are very good. you know a lot of popular culture. But there is another one that is a little bit behind the letters, but it's basically Gandalf, right? Gandalf. And you see Gandalf, as you say, this guy is a wizard. It's a white guy. It's got a big beard. And it's a white beard, white guy. He's a wizard, right? So it's something that, if you see a white guy in rose, with a white beard, trope, wizard. It's also called the wizard beard trope. Wizard bear trope is when the bear is so long that it hangs to your feet. Things like that. There are 50,000 tropes, lots of them. So you use them. They save a lot of exposition. They are also the building blocks of fiction. That's the thing we had at the beginning. Then from the tropes, we wanted to use the average reviews on the movies to eventually predict the cohesiveness and also the quality of the narrative, right? So we say, okay, so we want to put a model in which we say, here you have a set of tropes. What's going to be the rating of this movie? We still don't know how many Funko dolls we are going to sell with the movie, but I mean that's next thing. So basically, we want to train a neural net to predict rating from tropes. Right? So we have these tropes, this bag of tropes. This is the rating we're going to have, right? We had it in another paper. That paper was published. Was published last year. Essentially, we are optimizing a trope bag, right? So you see two papers. Essentially the data flow we're using exactly the same. The workflow we're using exactly the same. But Houston, we have a problem. It's not only a problem we have. I think that science has a problem. Even more so. I mean, there are many problems in science. Funding is one. Attracting talent in computer science is another. Because there are many computer science jobs and they're in high demand. It's almost impossible to attract anyone to low wages. I'm very uncertain career in academia. So I realized that the people who are, that's it's probably not politically correct to say, but the worst students I've had are the ones that are staying now at the university. And that's pretty bad. On the other hand, the best students, even the mediocre students, they are going to industry and they're collecting high wages. So it's not going to be nice for computer science in a few years' time. But still, you have to do what you have to do with what you have. And there are also many mental health problems. I mean, it's incredible the amount of people with anxiety problems, with stress problems, and that's being studied. And there are many. And they're also aggravated by the managerial style of many researchers. But the main thing is that we have a data problem. We really have a data problem. We can argue that all science is data science, because at the end, you have to collect data, process data, visualize data, and present data. And you have to do that pretty much with every kind of scientific endeavor you have, even more so in computer science. But it's very, very hard to have a reasonable way of dealing with data in an academic environment. Very recently, I was reviewing 500,000 grants for an agency here in Spain, and one of the sections of the grant was IP, intellectual property, and data management. The most imaginative thing I found was, we will buy a server with a big disk drive. That's what we are going to do with data. So I said, come on, I mean, we are in 2021. I mean, if you go with that to any, company, they will say, okay, next one, right? And of course, there is also COVID-19, right? COVID-19 meant that you had lots of data available from the genome of the virus itself to lots of data on infection, micro data. For instance, I in Mexico they are publishing micro data on all the patients of COVID. Also in Brazil, many other places. You had many things, and you had to have results, and you needed to have them now, and not only results. You need to use those results to take decisions, and do all kinds of things related to saving lives, which is the important thing, right? So, I mean, all became a crisis. I think it can be solved. In fact, data science has solved that problem. As I said, my daughter is working actually as an intern in a company, and they have all kinds of ways of dealing with data, and they are amazing ways, and they are everything is very structured, but as done in the industry. So that's the way it's done in the industry. It's not done in academia. I haven't seen the same level of expertise in data management in companies. I mean, in academia. Why is that? Well, because software development had a problem 20 years ago when we were using this kind of computers. Actually, we were using these computers in university like 10 years ago. I took this picture not so long ago. So, I mean, but I wanted to show it. It was running Windows 95 in the 2000. But, software development had a problem by the end of the century. All of a sudden, the 2000 bug happened, and many other things happened together at the same time. But they eventually solved the problem using the agile mindset. So there was lots of people, leaders from industry and proposers of different methodologies came together, and they proposed something that was called the Agile Manifesto. What is the Agile Manifesto? This is the Agile Manifesto. So it has like 4 things that are kind of preferences, right? So we like the thing on the left-hand side better than the thing on the right-hand side. So individuals and interaction over processes and tools. So they don't say that processes and tools are bad. They say, okay, we like processes and tools, but we like individuals and interactions even more. Working software over comprehensive documentation. So comprehensive documentation is good. You want to make a project, you create all kind of documentation, you work with it, okay, that's okay. I mean, if it works for you, it's okay. But it's much better that if you have working software every step of the way. Customer collaboration beats contract negotiation. So if you want to have to get the customer happy, whoever has, is going to be the customer for your software, you want to keep them happy, well, you need to negotiate all the time, not tell the customer, what do you want? I want that. Okay, so 2 years later, you have this. Is this what you wanted? No, it's not. Bad luck. And then eventually, the most important thing is that you have to respond to change over following a plan, right? So those are the 4 things, the 4 preferences, right, in the Agile Manifesto. Then there is a set of principles. I'm not going to go into that, but they're pretty much are the deals from that. Very interesting thing. I think it was a sea change in the industry of software, and pretty much everything that's on now is agile in one way or another. So you go to one company and you switch to another company. Pretty much the way they manage their production is going to be pretty much the same. I think that data science in industry works because it's agile. Data science is essentially software development, right? So they kind of tackle the problem or attack the problem of managing data and producing data in the same way that they would tackle any other software development problem, because it is a software development problem, essentially. What do I think we should do? We should make science agile. That's what I think I should do. I'm also going to take many personal stories, and I'm going to propose kind of preferences for doing this kind of thing in science. I'm going to call them hypotheses, right? So I'm going to formulate a series of hypotheses on how we could make science agile. And I'm going to tell several stories. Many of them are related to this paper. Some of them, are things that happen all the time. For instance, I never remember where's the paper that was accepted at a conference. I don't know if that happens to you. That happens to me all the time. So all of a sudden, I get an email, I've sent, 3 or 4 or 2 papers to different conferences, and I got a message saying, you got that paper accepted. I say, great. What was this paper about, and where was that? I use GitHub now. All my papers are in GitHub. So it's incredibly amazing the amount of data management and search you can say, putting everything in one place. Before I use grep in this drive, no problem at all. I mean, all the papers, or most of my papers, all the papers I convince my co-authors to do are in GitHub, are totally open. So just the only thing I need to do is search for them, right? So, that's only one of the advantages of having things in GitHub. It's open, people can collaborate with it. So data is also there. So data is there, it's in the repository. So this is my first hypothesis. Open over closed. So I think that one of the things that we should work in science related to data science, or any other kind of science, is work in the open, work openly. It's been proved repeatedly that open papers have more impact, but the fact that they are open, and using some mainstream standard site like GitHub opens all kinds of possibilities. You can use team working tools. You can be open to casual collaboration. You can do hackathons, anything like that. You can collaborate with other people. You can go in GitHub and say, so maybe someone else is working on this thing. So you can check it out in GitHub. It's there. Say, okay, interesting. I can work with them, right? But by opening everything. So you decide, I'm going to work on this paper. You create the repository in GitHub. You start working on the paper, on the scripts you need, software you need, everything, right? And that opens a whole lot of possibilities. For instance, you can interact with work using pull requests. Basically, pull requests are you are requesting other collaborators in the repository. You want to do this change. Maybe they want to accept it, or they want to comment or to whatever. It's an amazing way of working. That's the way they work in the industry. So they have a team. They say, okay, so we are going to work on this new feature. This new feature is going to be put into a branch. The branch is going to be eventually created into a pull request. All people check out, other collaborators check out the pull request. They review the code and they say, okay, this is okay. It's going to get in, right? So interaction is going to be via pull request. Interaction with everyone involved. So other students, PhDs, principal investigator, whoever. So it's very industry standard, and it's very stress-free. I don't know if you can have this experience with the students. They give you a paper. I haven't been using paper for quite a long time, but then you send it back with lots of red ink, and then they get the paper and they are a little bit like the cat in Shrek. A little bit like that. It's really stressful. I can empathize with that. So it's like you do your best to create the paper, you give it to someone who's a principal investigator or tutor or whatever, and you get back with lots of writing, and it's very hard. It creates a lot of anxiety. Reviews are not hard. Reviews are, okay, this is my work. This is what I want to do. Maybe you could do this a little bit better. Maybe you could do this a little bit better. This is probably not a good idea. Maybe you want to do it in a different way. It provides a standardized way of interacting with people. And of course, it's not totally stress-free. but it's much, the level of stress is quite reduced. And also, anyone can do a pull request. The principal investigator can do a pull request, doctoral student, graduate student, whoever, right? But you can also do many other things like issues. You can fork. You say, I'm not really, I'm not really great with this way of doing things. I'm going to do a fork. I'm going to try this different thing, and maybe eventually I merge it back. There are many ways, many things that you can do, right? And you also have free vulnerability scanning, right? So if you are doing GitHub comes with all kinds of freebies, and it's something that it's very, very easy to work with. These are all advantages you get for free when you are using something open. I said already that we published this paper last week, and then we got a call from Hollywood. We literally did. Of course, the people in Hollywood have some ideas in mind, right? But many other people, right? So we got a call from some small production company here in Spain, radios all over, of course, newspapers, but getting a call from Hollywood is a big thing. It should be some producer from Hollywood calls you and tells you, okay, so I want to do this small thing with what you do, which is not exactly what you had in mind, but maybe you. No, we can't do that. I mean, software development is never going to do that. Agile mindset is created so that you can respond to evolving requirements. So should be easy to work with evolving requirements. That takes us to the second hypothesis. Other collaboration over vertical chains of command, right? The stakeholder is essentially the world at large, depending on what you're investigating, researching, but sometimes it can be the public. If you are doing something that affects the entertainment industry, somebody would want to work with that. Somebody would want to, it's open. Somebody would want to, okay, maybe. So I don't have the capability for doing this myself because I don't know software development, but maybe you can do this, right? There are all kinds of people. And this is also a massive tool for management. You can involve all kinds of stakeholders through these collaboration tools, which are, as I say, industry standard, at least on the computer industry, right? So, and the key word here is collaboration. So all parties involved advance to a common goal. It's not like you have a plan. The plan is formulated by the principal investigator. You have to do this and then that, then come back to me. Send me the report. I will review, put it back. No, that's not going to work. It's not working, right? It's creating all kind of trouble all across the board. So I think that taking into account all stakeholders, it's going to improve not only the quality of life of researchers involved, but also the quality of life of the people who are paying us for doing research. Because I work in a public university, so it's essentially the European taxpayers who are paying for my. So you see, this second hypothesis is very, very incredibly powerful, but it's not enough. Another story related to this, right? So once we had published this paper, as I said last Friday, I took a look at the other papers that we had published. For instance, this one was a technical report. We published it in Archive. All the papers are, not the last one, but the others are actually in GitHub, so you can check them out. So I say, okay, so I need to change. I reviewed it. I say, okay, so what do we need to? Archive allows you the possibility of uploading things all over again. So, checking it out, seeing how everything was going, and so on and so forth, right? But when we were writing that paper, we had written another paper before, right? And the thing is that we downloaded all the tropes, and then all of a sudden some tropes had disappeared. I remember there was a movie that originally had like 900 tropes, and then all of a sudden it had gone down to 600. Another trope was appearing I remember 1,000 movies, and then all of a sudden it was only in 15 movies. I said, okay, it's almost impossible that this kind of thing happens. So you see that we were scraping data from a website, and scrape is an arcane art. It's something that you need to do very carefully. But any kind of data you receive, any kind of data that's updated, any kind of data that's really big data, because it's got velocity, variability, and so on and so forth, it's going to change. But there are many other things that can happen. For instance, I tried to run again this scraper we had. It's published as a Python library in PyPy, and then I got this error, file name too long. So I was scraping the same site, so it was exactly the same. All of a sudden, file name too long. As a matter of fact, this was a deeper problem that needed to be. Also taking into account that I am the supervisor of this thesis. Of course, I'm a stakeholder, and this is something that, in principle, well, maybe somebody else could do it, right? So maybe people are so lucky that they tell their graduate students, please do this. And I'm not so lucky. So I only have one PhD student. I had another one, but he was stolen away from me because, academia is terrible. But essentially, so if I wanted to check out everything and to produce a new file, I had to do it myself, right? Which is good. I mean, it was in GitHub, so it's Python. I mean, it's barely a language. Even a professor can do that. So, but that was its error, right? There was a deeper problem. I eventually fixed it, but what is quite clear is that sources change. Not only the source of the data that you are going to need, but also, in general, the source code of the thing you are working with. And you need to be very careful with that, because once you have proved a hypothesis, that hypothesis needs to be true, well, at least forever, right? Or you need to check that the data still adjusts to the initial hypothesis, and you need to prove that it still is happening the same, and that whatever you were saying or you were claiming is still a claim. So that takes me to the third hypothesis. You need to test at all levels, and that's much better than proving a hypothesis just once. In a paper, you say, okay, I have this data, I have these research questions, eventually I prove this, I mean, it's in a table, it's in a chart, whatever, this has been proved. That's okay, it's good, I mean, it's how everything works. But you need to test everything at all levels. You need to test source, you need to test source code, unit test, you need to test automatically your hypothesis. I mean, just imagine that the software industry had to test by hand everything that they produce. It would be totally impossible. You wouldn't have a continuous integration, you wouldn't have continuous development, but that's done routinely in science. You have a hypothesis, I mean, it's a statistical hypothesis. It's no big deal. It's you check this number, it's p minus than 0.005. It's okay. It's not. I mean, you don't need a statistician to check that out. This can be done automatically. Let's do it automatically. That's the third hypothesis. Then, with this paper that I just shown, I found that there was a bug. It was a small bug. I was using LaTeX. In fact, I was using something different to LaTeX, and that's a good thing. So using something called pweeb. Pweeb puts together LaTeX and Python, so the Python code is inside, it's embedded in the paper. So, but I needed to change that /ref. I needed to change it to site. That's easy. Am I right? Well, that seems easy. But there is a trope that's the nail. What's the name of it? It's the nail that the trope is called for want of a nail. It goes with that's for want of a nail. This was broken. Then the other thing was broken. So eventually said, okay, so I just wanted to change this, and then all of a sudden I broke the whole paper. Why? Well, data was important, but you could say it was open, right? So it's in the GitHub repo. It was developed using issues. So I said, okay, I need this issue. I created an issue for this thing I needed to change, and so forth. Also, it was tested. So why shouldn't it work? Why didn't it work? Well, dude, where's my data? That's another trope, by the way. It's called Dude, Where's My Car? And it comes from a movie that's called Dude, Where's My Car, which was taken from The Big Lebowski. It's an incredible movie. Dude, where's my data? So check out the source code in the paper. And the source code said this. You might see that the path to find the file says users/PhD. I did my PhD like 25 years ago. So that's not something that's in my, anyway, it's a local file, right? That wasn't a problem actually, because this file is something, it's called DB tropes. It's taken from IMDb. So it's something that you can download relatively easily, right? And it's also, it's dated and everything, no problem at all. The problem is the second one. The problem is the second one because it's a paper that's called tvtropes.json. That's right. I mean, that's a file we produce from downloading of the tropes. What was the date of that file? If I download it, am I going to obtain exactly the same thing? So everything was perfect. You get the file, you run pigweb, and then you produce a paper. But then all of a sudden, the tables are totally different. The charts are totally different. You have to change everything. For want of an ale, for want of changing site to ref, you change the whole paper. Eventually, I found it was in another repository, but that one was really, really hard. So fourth and last hypothesis, reproducibility and replicability. It's not the same. Sorry. Reproducibility is when you want someone else to reproduce your results. And replicability is when you want to do it yourself. It's much better than publishability. So what you need is to replicate first for your peace of mind. So you need, if you want to change just a single word in a paper, you should be able to reproduce it. But this happens all the time. So just imagine, I don't know if you have seen this, but how often have you yourself, or maybe you have seen someone else using PDF captures in slides in a presentation in a conference? Why? Because you produce a paper, you produce it with a script, or maybe not even with a script, you produce it, with some software for producing stuff, and then you get to the slides. You get to produce a slide for the conference. You don't remember how you produce this thing. Then what do you do? You take the PDF, you capture the PDF, and you put it there. Right? Okay. It's not the same. Sometimes in slides you need to make the letters bigger, or maybe there was an errata. Anything can happen. So replicability is very, very important. Data management and data visualization, and having all the data flows, all the workflow from the beginning, from the end, it's incredibly important. So those are the four hypotheses I think that will be part of Agile Science Manifesto. The thing is that doing science in the 21st century is a bit still like the waterfall. Waterfall was the methodology that was used. It was a methodology in which different parts of software development were totally divided. So you had a planning phase, then you had a development phase, then a quality assurance phase, and then eventually a deployment phase. Then everything came together into what is called DevOps teams. It's very sad that doing science in the 21st century is just like it used to be. It's a zero waterfall. So you have a plan, then you develop the software, you produce the thing, the report. But, well, we have created a series of hypotheses. We really need to prove those hypotheses right. And I can't prove them myself. I have a series of proofs that from my own experience, and I have been talking to you about that. But science needs to heal itself, right? It needs to kind of prove that this will actually work. What I'm going to propose is a series of steps that we could take to make this work. Or in any case, make oral workflow or the way we work as scientists much better quality research, and also better quality of life, which I think is very, very important. First thing, what is the product? So the thing is that in software development, it's quite clear what's the product. You're producing an application, you're producing a library, you're producing middleware, anything, right? Or hardware, software combination. So that's a product. In the case of science, it's not quite clear what's the product. So the product, what we are going to produce are reports for funding agencies, and we are also going to produce a paper or a series of papers, as many papers as possible. I think that we need to shift our way of seeing science so that we make the real product of science a workflow, where papers and reports are side effects. So you have a workflow, you have a way of dealing with data, reporting on data, visualizing data, and eventually proving hypotheses. But the workflow is the main thing. With the workflow, you can create a library, or you can set up pipelines so that those workflows work with other workflows. But I think that it's very important to realize that we need to have a workflow in mind. We are going to produce. I mean, the whole scientific team is going to be a team that produces a workflow, and then a side product we can produce papers and reports, but also other kind of things, right? With this, we should have reproducibility. I mean, remember the hypothesis, openness, because it's going to be open. The workflow is going to be running possibly on open hardware. Good thing about GitHub is you can run workflows for free. So this kind of thing that I have been doing now, I could perfectly be doing it in GitHub. I don't need not even my own. I mean, up to a certain level of computing requirements. But in many cases, you will be able to do it for free. It's tested because workflows need to be tested. Every one of the steps is to be tested, and it's open to collaboration because it's open. And it says open up opens up many different possibilities. You can create not only papers, you can create dashboards, you can create interactive charts, you can create APIs. That's been happening all the time with the COVID, because people not only have produced papers, they have produced websites, applications, dashboards, all kind of monitors. A few of them have emerged from academia, but most of them are, just regular people saying, "I want to do this. I'm gonna do this," right? You can code the workflow. In this case, this is actually taken from that paper. So we had a task in the workflow that said, build the paper in LaTeX for archive, and everything that needs to be done is there. So it's not even a README. The only thing I have to do is I get into the site and say invoke build paper LaTeX archive, and then it's going to be printing that message. It's going to be changing to a directory papers and doing pigweave and so on and so forth, right? So it's producing the paper. So you see that this is very, very, very easy. I can produce it. It's a workflow. It's a workflow that, in this case, the end of the workflow is the paper, but the whole it's a side effect. So the whole workflow, downloading the stuff, and it's somewhere else. And also, I would really encourage you to use things like Knitter. Knitter mixes LaTeX and R, pigweave, Python, and R, or R Markdown, which is very simple because it's only Markdown and R, and you can have a bibliography and everything like that. For instance, this is a part of that paper. The part that's highlighted right now is LaTeX itself, but then you have these. They are called chunks. These chunks which are written in R, right? And you give it a bit of metadata and a name and so on and so forth, and then inside you put any kind of R script that's going to produce it's going to produce the chart anytime you want. In principle, you could do anything you want. You could process data. You could even obtain the data from an external source. In this case, well, it was very easy for me, or it would be very easy for me to produce a different chart with a different way, because there is a simple command that extracts all the R from the latex, and then you create a different script with the R, and as a matter of fact, this paper has been rejected a couple of times already, so we gotta do something about it. But we have been using it in other papers all the time, using meter. Second thing, a second way of proving the hypothesis. Who owns the product? There is a role in Agile, in the Agile way of developing software that's called product owner. Product owner is, in a way, it's the person who calls the shots. If something needs to be decided, he or she had to say, okay, this is how it's going to be, right? So he might be the person that's going to decide how to prioritize some features over others. And then who is going to be that person? I think that the person that needs to be the product owner is the, let's say, the person who had the idea. Or because basically the person who has the idea is the person that knows better what's going to be, has the vision. I mean, the product owner has to be the person that has the vision of how the product that's going to be a workflow is going to emerge. So that's a person that needs to be there, right? So this is, well, it's not related to reproducibility. We don't care, or replicability. Care about that, but it's open. You can do tests because you can kind of say this new feature needs to be done, and then you need to check whether that feature is actually working. And of course, it's open to collaboration because there is not a vertical chain of command. A product owner is a person with a vision, right? And there are some rights that person has, but they don't have any kind of power over the rest of the team. In our case, for instance, it's a doctoral student that's owning, in this case, his thesis. Ruben, who is the person who's doing that, has this Kanban board. You see that there is a private there. I still haven't convinced him to make it public. But still, you can work almost the whole 9 yards with having a private repository, because you can eventually make it public. You can also have the most of the tools, all the development tools. You might not have collaboration from other stakeholders, so that's not really amazing, but we're working on it. So I think I will try to have Ruben next week liberate it. But you see that he's owning the product. He's using a Kanban board. This Kanban board said, okay, this is the backlog. This is what I need to do. And it's quite clear for everyone involved, in this case, him and the two tutors, what's going on, what's going to happen, what needs to be done. We can suggest prioritization, and we can do anything we want using this thing. Good thing about this person, he's actually working as a software developer. He's working for a company. So this is natural to him. Probably it's not so natural for people who have been in academia their whole life, but I think it needs to be, because it's really worth the while. Then eventually, the thing is that we need to use common software development tools and common best practices, because they are there. They are, in most cases, they are free. It's open source, so why not use them? So instead of having no, I still like paper. I like red ink. I mean, that's not going to cut it. I need to, I need my student to be present. I need to look over his or her shoulder to see whether they're working or not. Working remote, we have remote collaboration tools. I mean, it works for the software industry. Nowadays, all companies all over the world, Microsoft, Amazon, Google, they have remote people working everywhere. Why shouldn't it work for a PhD student or for someone that has been hired for a project? With that, you got reproducibility. Why? Because they are common tools. They are open source. You say, I'm using this. I'm using Python. I'm using this library, that library, and then I'm using this pipeline. I'm using, PyTorch or whatever. You can use the same. Just download it. This thing. You have this workflow. Download the workflow. Run the workflow. You have it. It's open, right? Because most of these tools like GitHub, GitLab, Bitbucket, they're open. You can run tests. You can do it automatically. You can do it systematically, and that's incredibly important. It's open to collaboration. So good thing, right? So we should also use industrial, best practices, right? Common industrial data science best practices, which are things like CI/CD workflows, using MLflow. MLflow is out there. It's something. It's an incredibly helpful tool to run workflows. There are many things that you could use. For instance, code smells. I've been working for a long time with. I have been giving tutorial on programming evolutionary algorithms, which is my main thing. I still, it's increasingly easier to find quality code, but it's still not, the mainstream thing. People don't avoid the smells, and there are industrial tools. There are many tools that can check your code and say, okay, this is good code, this is not so good code. Best practices are very important. You can simply take someone who has been working for the industry for any length of time, and then all of a sudden tell them, no, you forget everything. We do it this way. We don't use source control. We don't use tickets or Jira tickets or whatever. We don't use code smell. Just, you program, it works. Run it once, more or less works. Yeah, no problem. Configuration, no, you change this in a program file, in a code file, you run it all over again. There are some security issues. Well, I don't care a lot, right? You simply can't do that. If we want to attract talent to academia, we want to keep talent in academia. If we want to create quality workflows and we want to achieve excellence, in the world we live, I think we need to do this. We need to follow data scientists in companies. There is a big hurdle, or there are many hurdles, of course. There are always many obstacles to change. But I think that the biggest hurdle is changing from pay to publish to pay to deploy a workflow. Because right now, essentially the industry, the biggest industrial science publishing complex, which is reduced to, I think, like 2 companies right now, you pay to publish, right? Conferences are essentially that, so that kind of thing. Pay to deploy workflow is not so different, actually. So you are in the case of PDFs, you are consuming storage resources. In this case, you might be consuming some computing resources, but I think that would make it incredibly helpful for everyone. Just imagine that I have this trope thing, and then all of a sudden I publish it in any place. I say, okay, so here's my workflow. So what do you need to work this workflow? You can download it, you can run it yourself, or maybe there is this hosted version. We have paid Nature or Public Library of Science or Springer or whatever to host it, and you can run it. So you use this API endpoint, you run it, and that's it. So I think that would be really amazing, and I think that's probably where we are going, some way or the other. So I'm about to finish. So what I am going to ask from you is to really join the Agile Science Manifesto, which is actually kind of a thing. So in the same repository that I have this presentation, I have drafted an actual manifesto with 5 pages. You can check it out, and I really invite you to check it out and maybe add things, suggest things, whatever, via pull request. What do we want to do? We want to make science more open to everyone, open to society, open to all stakeholders, open to everyone. More adaptive, so that we can really respond to challenges that are maybe a little bit related to what we do, but the society really, really needs, and also sustainable. And this is the most important thing. So to make it sustainable, you need to keep producing the same results over again, even when your PhD has gone to industry, because he was being paid peanuts, and any mid-sized software development company was paying them twice as much. Even if you have you have a lot of time, anything important is sustainability. You need to produce more results over the same data over and over again. I think that we should leave waterfalls for rainbows. Waterfalls are a very beautiful thing, but we should leave them for rainbows. We shouldn't use it for science. Software development industry has done it. It's almost completely ditched. I think that we should make science agile. And that's it. Thank you very much.
Thank you, Professor. Thank you. It's exciting.
Okay. Thank you. That was inspiring.
Thank you.
Yeah. And I related so much to it. I've also been in academia for 25 years, and it's like, where is that data set? Is it SharePoint, a Dropbox, GitHub? I mean,
No, it's in it's in a disk drive of these graduated students who left 2 years ago, and then what do you do? Yeah,
right.
exactly like.
Right. And then there's always the fear, might GitHub ever go away? And then what do we do?
Yeah.
So I'm going to open it up to any questions from the audience. Please feel free to unmute and ask your question if you have a question.
I have stopped. I have problem with the sound. So please also kind of type a summary of any questions so that I can say completely.
Okay.
Now it looks like it came back.
Okay.
So it's okay now.
So one of the questions that I have is, it seems like, especially even with public funding for universities, it seems, I don't know what year it happened, but when grants are given to, universities to conduct research, I don't know. It looks like you. Oh, can you hear me? Okay.
Yeah, I can hear you now.
Okay. Yeah. It seems like, once they got into the whole patenting idea, everything really became more closed sourced and protecting your work rather than sharing it. And so I don't know if, I was thinking what you were saying, if you're the product owner, you have the idea, you own the product, and how you prove that. And I was thinking blockchain, as a means of kind of protecting your work, but still keeping it open because of, a ledger that's you're not able to tamper with, and you could prove that, you came up with the idea first, or I don't know. I was wondering if that has come up in concerns of being the product owner and proving it, I guess.
Well, if you are using some source management system, which of course can be game, but still, very clearly who's done everything. You can use a command that's git blame, and it tells you every change in every file who's done it. So that I mean, if you're worried about the affirmation of ownership, that's something that you can do relatively easy, and it's much easier. In fact, that if you are without Word file putting it back and forth. But on the other hand, it's no problem with keeping it private. I mean, if you look at companies don't have all their products in GitHub. I mean, they have it in GitHub, but it's private. So even if you are going to keep it private, you can still use the same tools. You will not, as I say, be the whole totally open, and being open has many advantages. But still, you're going to achieve most of the things. So I think that the takeaway message is let's work as they do it in the industry, essentially. I think that's going to be better for everyone. So it's going to solve many problems that we have. Of course, we need changes, but drawing from their experience, using their tools, I think that that's going to be good for everyone. No? For everyone who's entering academia right now or who is still in academia. If nothing changes, I'm going to be in academia for some time. I have a question here. I mean, thank you very much, Ariel, for your kind words. It says, can you describe the pay-to-deploy workflow again? I don't understand how it will work. Think about some services like, for instance, Amazon Lambda. So essentially, Amazon Lambda, what you have is you deploy a function, and that function is deployed, and every time it's called, you get charged a certain amount of money for seconds, right? So pay to deploy would be kind of a flat fee. You have a workflow. You describe it in industry standard terms, as you would do something you deploy to the cloud, maybe a Docker file or maybe a set of Docker files. The author should be paid. That's a good one. I would really love the authors to be paid, but unfortunately, the science publishing industry doesn't work that way. So usually pay to publish. But of course, I mean, you could think about some schemes in which you should be able to publish, let's say Nature or Springer or whatever. You pay an upfront fee, like, whatever they decide. And then you say, okay, so this is incredibly valuable. And it's not all open. Maybe there is some intellectual property here that I want protected. I'm going to charge for that, right? So the publishing conglomerate should say, okay, so you want to publish it. It costs you so much up front, but then you're going to be paid every time it's used. So it would be having in academia so long that being paid for publishing is not something that I even consider. It's a very good idea, Omar. Thank you very much.
Are there any other questions? Keeping an eye on the chat there. Okay, so if we can just, we'll get your email out if you're okay with that, or contact information in case.
Yeah, of course.
Yeah,
By all means.
maybe either you can drop it in the chat or we could circulate it afterwards.
Sure.
But this was great. Thank you so much.
Thank you, Professor.
Thank you very much.
So we are going to close up the
Thank you, Professor.
event. Yes. And I'm going to just share our final slides here. So first of all, we really want to thank you, big thank you to all the speakers. I think there's, I've been getting feedback, and we definitely have heard that it's there's a lot of the audience members have already been inspired and are reaching out to some of the speakers, or really want to see the recording so they can really absorb everything that they've heard in the last couple of days. So thank you so much for your time and your inspiration. Just to kind of wrap things up, we want to make sure that you're aware of the programs that we have here at Southern. So yesterday, if you joined us at the end of the day, you heard about our data science initiatives at Southern. So we do have a bachelor's in data science that's offered jointly with the computer science and the math department, and the link is right there to learn more. We have a minor in data science. We have now an approved graduate certificate in data science 12 credits and a professional master's degree in data science that's coming soon. If you have any questions about them, please check out the our two contact people. These are our data science coordinators, Dr. Imad Antonios from the Computer Science Department and Dr. Aaron Clark from the Math Department, and both of their email addresses are there, and they're also on the link, the data science link for the BS in data science. And with that, we want to also ask you at this point, I put in the chat a link for our last speaker's evaluation of the last speaker. And again, this is really for us to generate a report overall for the department that funded this workshop. And also I have the QR code here to get you to our evaluation form, which is just a Google form to get your feedback. It shouldn't take more than 5 minutes to complete. It's a quick overview. And also, if you've been inspired by this, as Dr. Shada mentioned in the beginning to start off our day, if you have ideas of other seminars that you would like to see, maybe something in a particular domain, or please let us know, because we would love to continue to offer these. There's the bit.ly link there for Advanced Computing and Data Science Evaluation, and the QR code. And I think that's it for us. Dr. Shada, if there's anything, I think I'll let you, since you inspired us to get this, you were the idea for this seminar series. I would just like you to close, and if there's any questions that you might have for folks, we'll include follow-up through our email on Eventbrite on how to contact both of us, and also we'll explain to you how to get to the recordings and all of the speaker slides as well. So that's coming, and we hope to post that out to you by Monday with links to those. So I'm going to turn it over to you, Ala, and
yeah, thank you, Lisa. Actually, I would like to thank everyone who dedicated time to come and share with us this opportunity. It was really a great pleasure, and your attendance made this event a great one, and we thank you all for that. We would like to thank also our guest speaker for their time and wonderful talk, and we would like to thank our provost. We would like to thank our faculty members. It's really a collaborative effort, and we had lots of discussion at our department about it. And we hope to see you in the future in other upcoming events. And please, you should get an email with evaluation. So please let us know about your feedback. That really means a lot for us. And maybe in the future you will join us at Southern for some of our program, and we will be delighted for that. Thank you.
very, very good. All right. Thank you all, and enjoy your day, evening, whatever time zone you're in. I know it's late for many of you, so good night, and
All right.
thank you.
Thank you. Thank you, Binlen. Thank you so much for coming.